Hi everyone, welcome to GrayHat 2020. My name is Hardik and I welcome you all to our training titled Fuzzing and Finding Vulnerabilities using AFL and WinAFL. This is going to be our overall agenda for today's training. We will start with introduction and then I have divided this training in three parts, part 1, part 2 and part 3. In part 1, we will see what is a vulnerability, what are different types of vulnerabilities, what is fuzzing, what are different types of fuzzer, and what are the steps involved when you want to fuzz a program. We will also see what is crash tries and root cause analysis. In part 1, I will be having a very simple exercise in which I will give you a simple C code and you need to find different types of vulnerabilities. Then in part 2, we will see what is AFL, how does it works, and how do we fuzz a simple C program using AFL on Linux. We will also see what is root cause analysis and how do we do it using GDB. We will also see crash triage and we will use a tool called crashwalk for that. After that, we will move to part 3 in which we will see what is WinAFL, how does it works, what are the difference compared to AFL on Linux, and then we will fuzz a simple C program using WinAFL on Windows. After that, we will do root cause analysis using WinDBG, and in some cases, if possible, we will see how do we debug a program using Visual Studio. After that, we will first some real-world softwares, and we will also discuss root cause analysis of two vulnerabilities which I have found and reported. After that, we will move to conclusion. So the key takeaways from this training will be understanding of different types of vulnerabilities, understanding what is fuzzing, how does fuzzer works, and what is AFL, what is WinAFL, and how does they work on Windows as well as on Linux operating system. This training will also give you a basic understanding of what is root cause analysis, what is crash triage, what are tools involved in that, and how you can do it yourself. I hope that you will find my training useful. And with that, let's start. So just to give you a brief introduction about me, my name is Hardik Shah and I work as a security researcher at McAfee. I do vulnerability, exploit and malware analysis on a day-to-day basis, and apart from that, I do fuzzing and bug hunting. As of now, I have around 24 CVEs in my name from various vendors like Microsoft and different open source softwares. I was also MSRC 2018-19 Most Valuable Researcher, and I was also in MSRC Q1 2020 Top Contributing Researcher list. I write blogs on various threads from exploit vulnerabilities to malwares, and if you are interested, you can go to this URL and you can read my blogs. You can also follow me on Twitter. My Twitter ID is Hardik05. So this is our agenda for part 1. First, we will see what is a vulnerability, what are different types of vulnerabilities like integer overflow, integer underflow, stack and heap overflow, out of bound read, out of bound write, use after free and double free. After that, we will do a very simple hands-on exercise in which I will give you a very simple C program and you need to find different vulnerabilities by manually looking at the code. After that, we will move on to fuzzing. We will start with why do we need fuzzing, what are different types of fuzzer, and then we will see what are the steps involved when you want to fuzz a program. We will also discuss about crash tries and root cause analysis, and we will also discuss how do you report issues to vendor and what are the different bug bounty programs. Let's start with the basic. What is a vulnerability? A vulnerability is a bug in the software which can be used to perform various unwanted activity on a user's system. They can be of different types like remote code execution in which someone can execute malicious code, or they can be of type denial of service in which someone can crash the software or entire system, or they can be of type privilege escalation in which someone can use vulnerability to gain access to the higher privilege account. Now, vulnerability can be used in different types of malicious activities, like they can lead to system compromise, or they can lead to installation of ransomware, Trojan, botnets, Bitcoin miners on the system, or they can lead to data theft. Vulnerable software can also have huge impact on the different industries. They can lead to data theft if someone exploits them, or they can lead to loss of productivity when someone exploits and make their system unusable. They can lead to loss of productivity and loss of revenues. So let's go ahead and see what are different types of vulnerability. So in this training, I will be covering some of the common vulnerabilities which we have found in the field, like integer overflow, underflow, stacked and heap overflow, out of bound read, out of bound write, use after free and double free. So let's start. Now let's see what is an integer overflow. An integer overflow is a vulnerability in integer data types, the way in which they store the data. If you have done some programming in C or C++, you may be aware that there are different data types like integer, character, float, long, double, etc. And each of these data type has a specific size. In case of integer, there can be two types of integer. First one is unsigned and second one is signed. So unsigned integer means it will save all the positive value, while if you want to store some negative values, then you need to use signed integer. So when you declare an integer as unsigned, it means that it will store only positive value. But when you declare an integer with keyword int, then it means that it can store both positive and negative values. Now, how does a program determines whether an signed integer is positive or negative? So they uses a very simple logic in which the most significant bit is used to denote signedness. Since the size of integer is 4 bytes, so if you convert 4 bytes, it means that there are 32 bits and each of these bits can denote two values. It can be either 0 or it can be 1. So maximum possible value an integer variable can hold is 2 to the power 32. In case of signed integer, the first bit from the left, that is most significant bit, is used to denote signedness. So if this first bit is 0, it means that the number is positive. If the first bit is 1, it means that the number is negative. So in case of signed integer, we only have 31 bits to denote the number. So based on that, the maximum value for a signed integer will be 7f and maximum value for unsigned integer will be ff. This is because for unsigned integer, all the 32 bits will be used to denote the number, but in case of signed integer, only 31 bits will be used to denote the number and 1 bit will be used to denote the signedness of the number. Now let's see what happens in this case when you declared one variable as unsigned integer and it already contained the maximum possible value for an unsigned integer, that is ff, and if you add 1 to that. As you can see on the right hand side, when you convert this value to binary, it becomes 1111. So basically there are 32 bits and each bit is 1. If you add 1 to that, it will simply add 1 plus 1 0, 1 carry will come over here. It will again become 0, 1 carry will come over here. Similarly, moving forward, the carry will come over here and it will become 1 plus 1 0, 1 carry will come over here. So this is the end result. But if you count the bits over here, these are 33 bits. And since the size of integer is only 4 bytes, it cannot hold this last bit. So what it will do is that it will truncate this last bit and it will save the remaining data, that is 000 over here. So in this case, the result will actually become 0 because carry 1 bit will get truncated, and so this can cause various issues in the program. Similarly, when you declare a variable as signed integer and if it contains the maximum possible value for a signed integer, that is 7f, and if you add 1 to that, then the result will become negative and it will cause various issues in the program. Here is a very simple example. As you can see it over here, there are two variable, variable 1 and variable 2, and then there is third variable which is size 1, and its value is derived by adding variable 1 and variable 2. Then there is a malloc call which uses size1 as a size parameter, and then there is one mem copy which copies some data to this newly allocated memory by malloc. In normal circumstances, this program will work absolutely fine, but in case any of this variable, that is variable 1 or variable 2, contains the highest possible value for a signed integer, that is 7f over here, and if something gets added to that, then result will become negative, and when you pass a negative value to malloc, it will not allocate any memory, so this buffer 1 will point to null. And if there are no checks in the program which checks if malloc is successful or not, and if they use this memcopy instruction, then this will lead program to crash. There is a very simple real life example of a similar bug in VLC media player. This bug was actually in parsing of MP4 file. As you can see from the code over here, there is an unsigned integer variable ilength, and then there is again another unsigned integer variable named I. You can see that there is a malloc call over here which expects a parameter that is ilength plus 1. So in normal circumstances, this program will work absolutely fine. But in case ilength contained the maximum possible value for an unsigned integer, that is ff over here, and if you add 1 to that, then result will become 0 as we have discussed over here, and in that case malloc will fail. And as you can see that there is no check in the code to see if malloc is successful or not, and in the code the values getting access to this newly allocated buffer over here. But in case this buffer or this memory was not allocated, this will lead to program crash over here. So this is what an integer overflow is. Now let's move on to next topic and see what is an integer underflow. As we have seen, in case of integer overflow, size of integer is 4 bytes, and the range for signed integer is from -80000000 to 7f. It means that a signed integer can hold the minimum value, which is this, and maximum value is this. Similarly, for unsigned integer, the range is from 0 to ff. So this is the minimum value which a signed integer can hold, and this is the maximum value which a signed integer can hold. Now what happens in this case when there is one signed integer and it already holds the minimum possible value, that is -80000000, and if program subtracts 1 from that. Let's see it on the right hand side over here. When you convert 80000000 to binary, it will become something like that, where the most significant bit is 1 and rest of the bits are 0. If you subtract 1 from that, then it will borrow 1 from here and it will come over here, and so the rest of the bits will become 1 over here, but the most significant bit will become 0. As you might have noticed over here, there is a change in signage because 1 means negative, 0 means positive. So from the lowest possible value, it becomes the highest possible value over here. And this can lead to various issues in the program like infinite loops or malloc failures, etc. There is a very simple example over here, as we have seen in integer overflow case. Same example is over here, but only difference is that the size 1 is calculated by subtracting variable 2 from variable 1. So in this case, what will happen if variable 1 already contains the minimum possible value, and if variable 2 contains 1, then size 1 will become a very large positive value, and in some cases malloc tries to allocate that much amount of memory, and if malloc fails and if there is no check that memory allocation is successful or not, and program tries to copy some data to the unallocated buffer, then that can lead to program crash. So this is what an integer underflow is. Now let's move on and see other types of vulnerabilities, that is stack overflow and heap overflow. A program follows a specific memory structure in which some memory will be allocated for kernel and kernel data types, then some memory will be allocated for stack, heap, data, and text. To understand stack buffer overflows, let us first see how does a function calling works. When you call a function inside your program, the program saves the address of the currently executing instruction onto stack so that when function finishes its execution, it returns to same address and resumes its execution. Now, since that address is saved on the stack, if there is any way by which someone can corrupt that address, then when the function returns, program will go to that corrupted address and that may lead to some undefined behavior, or it may allow someone to control the execution of the program. When you declare any local variable, they are stored on the stack and they are of finite size. In case someone overflows those variables, then there are chances that the return address which is saved on the stack gets overwritten, and that will actually lead to the program corruption. Let us see a very simple example over here. As you can see, there is a function foo and it has two character variable, variable 1 which is of size 8 and variable 2 which is of size 100. You can see that there is one memcopy function call over here which copies data from variable 2 to variable 1. Since the size of variable 1 is only 8 bytes while the size of variable 2 is 100 byte, this will lead to a classic stack-based overflow, and this will lead to corruption of return address which was saved on the stack. So when the program returns from this function call, then program will try to go to that corrupted return address, and that will lead to unexpected behavior or some crash in the program. There is a very simple real life example over here. This is again from VLC. As you can see, there is one character array and its size is maximum, that is 128 bytes. There is another variable that is of type signed integer and its value is getting read from RTSP header. Now, if the value of this name length becomes more than 128 bytes, then it may lead to a stack-based buffer overflow. As you can see it over here, there is a memcopy function call which is copying some data from buffer plus RTSP site size to new sender name, and the length is defined by name length. So if this name length is more than 128 bytes, then this may lead to a stack-based buffer overflow. Stack is used by programs when size of local variable is fixed and program is aware of those size. But in case the size of variable are not fixed, then program uses dynamic memory allocation functions like malloc, calloc, reloc, etc. When a program allocate memory at runtime using such functions, the memory will be allocated from the heap, and heap maintains a data structure for memory allocations. In case some memory gets freed, then program will update those data structure. It will mark those memory as free, and when it allocates some memory, it will mark that particular area as allocated. If any overflow happens inside heap buffer, then there are chances that may lead to corruption of this data structure. This will lead to undefined behavior in program or program crash. A very simple example of heap overflow is shown over here. As you can see that variable 1 stores the dynamically allocated memory of size 8 using malloc, and there is another variable that is variable 2 of size 100. Then there is a memcopy function call which copies variable 2 data to variable 1. Since the variable 1 is of size 8, and when memcopy copies 100 bytes of data to this, then it will lead to heap buffer overflow, and that will lead to program corruption or undefined behavior. So this is what stack overflow and heap overflow. Now let's move on to another topic, that is out of bound read and out of bound write. An out of bound read or write error occurs when a program tries to access memory which is beyond allowed limits. It can be out of bound read or write in stack, or it can be out of read or write in heap. For example, as you can see it over here, there is an array variable of size 10, and later on in the program tries to access value at 100 index. So in that case, it will be an out of bound read because program is trying to read memory at 100 index of this particular array whose size is 10 bytes. Later on, if the program tries to write some data at 100 index of this array, then that will be treated as out of bound write because the size of array is only 10 bytes, but program is trying to write data at hundreds index over here. Same case is for heap memory as well. Only difference is that in case of if the memory is dynamically allocated, so as you can see it over here, there is a malloc call which allocates 10 bytes of memory, and later in the program tries to read data at 100 index. So that is an out of bound read inside a heap memory, and later on, as you can see, program tries to write data at 100th index. So that is an out of bound write in heap memory. Now there is a very simple example which I found in libgd. So as you can see it over here, there is a variable named buffer underscore caret. Its value is getting increased every time. So this is inside a loop which I have to truncate because of space constraint. So as you can see that this variable is getting used as an index to this array, that is decompression buffer. Now in situation where value of buffer caret is more than size of decompression underscore buffer, then this will be an out of bound read issue. Similarly, you can see it over here. There is an array that is bitmap, and there is another variable that is bitmap underscore caret. So if the value of bitmap underscore caret becomes more than size of bitmap array, then that will be an out of bound write issue. Now let's move on and see what is use after free and double free. A use after free vulnerability occurs when a program tries to use a memory after it has been freed, and it can cause program to crash or have some undefined behavior. A very simple example has been given over here. As you can see that there is a memory which is getting allocated using malloc call, and later on this memory is freed. Then program again tries to use this freed memory over here, so that will lead to a use after free vulnerability. A double free vulnerability occurs when program tries to free allocated memory multiple times, and that can cause a program to crash. For example, as you can see that there is a memory which is getting allocated using malloc call, and after that memory has been freed. But when that program again tries to free that memory, then that will be a double free vulnerability in the program because the memory has already been freed, so it cannot free it again. Here is a very simple example of use after free vulnerability. This vulnerability was in libtiff. As you can see it over here, there is a buffer which is getting freed, and later on in the program, the buffer variable is again getting used. So since the buffer is already freed over here, it cannot be used, and so this is a use after free vulnerability. If you want to know more about this vulnerability, you can go to this link and read more details. Let's move on and see what we have learned so far. So we have seen what is a vulnerability, what are different types of vulnerabilities like integer overflow, integer underflow, stack heap buffer overflow, use after free, and double free. Let's move on and do a very simple exercise. So what you see on the screen is a simple C program which contains a lot of vulnerabilities. What I would like you to do is go through this program and try to figure out what are the different kinds of vulnerabilities which are present in this code. As a hint, all these vulnerabilities we have discussed in last few slides, so it should be very straightforward and easy for you. So let's go ahead and see. As a hint, There is one vulnerability in this part of code. There is another vulnerability in this part of code. There is another vulnerability over here and here. I think many of you might have figured it out already. If not, then let me go through them. As you can see, there are different vulnerabilities over here. So first one is over here, and it is an integer overflow. As you can see that there are two signed integer, they are getting added, and then there is a malloc call over here, and then there is one memcopy call over here. So this can easily lead to an integer overflow, as we have seen in our last few slides. Then there is another vulnerability over here, which is an integer underflow. As you can see that two values are getting subtracted, and then there is a malloc call, and then again there is a memcopy instruction over here. And there is a third vulnerability over here, which is a double free. As you can see that the buffer one is already freed over here, but here the program is checking if size one is even. If so, then it will again free the buffer one. So this will lead to double free because buffer one is already freed. And last one, you might have already figured it out. It is an use after free because buffer one is already freed over here and program is trying to copy some data to that. So this is a use after free vulnerability over here. I hope that this exercise has given you a good understanding of different types of vulnerabilities. Now let's move on and go to next topic, that is bug hunting and fuzzing. As we have seen last time that manual code audit will take a lot of time and it's very slow. Also, it is not possible to cover all the code parts. And if the code base is very large, like if it contains thousands of lines of code or millions of lines of code, then it is not possible for a single person to do all the audit. It is also not very productive because someone has to go through all the code manually and try to figure out what kind of vulnerabilities are there. And so it may be possible that various things can be missed during the review. And it is also not possible to cover all the scenarios. So we need a way to automate this task, and that is what we call as fuzzing, because if we automate this thing, then it can cover most of the code parts and we don't need to worry about the size of the code, and it can be done by a single individual. It can be also automated further to notify about crashes and issues. Now let's move on and see what is fuzzing. So fuzzing is a process of automated bug finding in the program, and it consists of various steps like feed input to program and then monitor it for any kind of crash. If we find that any particular input is crashing that program, then that test case needs to be saved. And after that, we need to generate a new test case, and we again need to repeat the same process, that it feed that test case to program and monitor for any crashes, save that test case and generate new test case and repeat it. So that is what we call as fuzzing. As you can see in the image over here, when you give an input to the application, it takes code path 1 and it gives output 1. When you modify that input and you give that again to application, then it takes code part 2 and it gives output 2. But in an unexpected case, what happens is that the application will first take code part 1, it will go to code part 2, and that will lead to a crash. So this is what a fuzzer does. It will modify the test case and it will monitor the output and it will see if the program crashes or not. Now there are various types of fuzzer. So let's go ahead and see what are the different types of fuzzer. First, let's see what are dumb fuzzers. So dumb fuzzers generates random input and they don't have any understanding of file format or network protocol or the application which you want to fuzz. They will simply generate some random inputs and they will feed it to the program and they will monitor it for crashes. If the program crash, then they can save that input, otherwise they will again generate some random inputs and they will keep feeding it to the program. One example of dumb fuzzer is Radmasa, which is available on Linux. So it generates random inputs which you can use and you can see if your program crashes or not. But there are certain issues with dumb fuzzers, like they can take a lot of time because they don't know what is the file format, or they don't know what is the network protocol structure, or they don't know what all the paths the program is tracking. So they can take up a lot of time unless you are very lucky where it generates some input and your program immediately crash. Now let's move on and see what is a generation fuzzer. As we have discussed, dumb fuzzer generates random inputs, and in some cases they may not be very effective because if the program is checking for a particular file header or a particular type of network packet, then the input generated by dumb fuzzer will be discarded. So generation fuzzer is useful in that case because they will generate input based on a predefined templates. Generation fuzzer will require understanding of file format as well as network protocol, and some example of generation fuzzer are like Peach and Suli. So if you want to use any of the generation fuzzer, you need to provide some predefined template. Based on that, generation fuzzer will generate new inputs. If you want, you can try Peach and Suli. Let's move on and see what is coverage guided fuzzer. As we have discussed, dumb fuzzer generates random inputs which in some cases can be discarded, and generation fuzzer will require understanding of protocol or file formats. Coverage guided fuzzer uses a concept called instrumentation by which they can monitor the execution flow of the program, and based on the execution flow they can modify the input accordingly. So in coverage guided fuzzer, you don't need any knowledge of file format or network protocol. Coverage guided fuzzer mutates the file and check for new code path or any crash. If they find any new code path, then they will add it to the queue. If they find any new crash, then they will save the input. Example of coverage guided fuzzer are AFL, WinAFL, HongFuzz, LibFuzzer, etc. There is a very interesting case study done by author of AFL in which he created a simple text file which contains only hello, and he feed that text file to an JPG image program. And when he ran that fuzzer for few hours, he found that the fuzzer automatically generated few valid JPG files out of this hello string. So that is the power of a coverage guided fuzzer. If you want to know more about this, then you can go to this URL and you can read in details over here. With that, let's move on and see what we have learned so far. We have discussed what is fuzzing, what is bug hunting, and what are different types of fuzzer like dumb fuzzer, generation fuzzer, and coverage guided fuzzers. Now let's see what is coverage and instrumentation. First, let's discuss what is basic blocks and coverage. So a basic blocks is consecutive lines of code with no branches, and a basic blocks have an entry point and an exit point. Entry point is the point to which control comes to this basic block, and exit point is the point from which control goes to another basic blocks. There is a simple C program over here. As you can see, it contains different lines of code, and as you can see, there will be three basic blocks because as you can see, there are few variables which are declared over here, and after that there is a condition that if x is greater than z, then controls come to this block, and there is a else condition which will be taken when x is less than or equal to z. So this will be another basic blocks. So a basic blocks is a consecutive lines of code which doesn't contain any conditional branch. In this case, the basic blocks will be this one because if you see over here, there is no conditional jump. And as soon as there is a new if statement which leads to a jump, there will be another basic block. When you disassemble a program, you will see the basic blocks like this, as you can see it on the right side of this slide over here. And as you will notice over here that the only jump instruction is at the end of the basic block. So this is what a basic blocks looks like when you disassemble the code. Now there is another topic, that is code coverage. So code coverage is a measure of code which will be covered by a particular input. When you give a input to this program, this simple C code, then it can either cover part which is inside if, or it can either cover part which is inside else, but it cannot cover both of these together. So we need two inputs to cover all the parts in this code. A coverage guided fuzzer uses binary instrumentation to measure code coverage, and based on the code coverage, it modifies the input files so that it can cover various parts of the code. With that, let's move on to next topic, that is instrumentation. Now, here is a very simple question. How do you trace the program execution at runtime? If you have a very simple C program like this, which contains various functions, what you can do is that you can add a printf code and you can debug that, but then it won't give you much data. You cannot automate different things with that, and you need to do a lot of manual work. So there is another technique which is called compile time instrumentation. And in compile time instrumentation, what happens is that the compiler adds instrumentation code at compile time, something like this you can see over here. So this is a disassembled code, and when you disassemble a instrumented binary, you will see some codes like this. So this is from AFL, and when you use compile time instrumentation, they help you in automating various things like code coverage measurement, and they remove all the manual efforts. So that can be very useful. This is what AFL uses. We'll be talking about that in next slide. And in case the source code is not available, say on Windows, then in that case you need some tool which perform runtime instrumentation. So for Windows there is one tool which is called DynamoRio, and it does runtime instrumentation. We will be talking about that in part 3 when we will discuss WinAFL. Let's move on and see how does AFL binary instrumentation works. So AFL adds compile time instrumentation, and what it does is that it adds a random unique ID to each block. It will generate a unique ID. For example, as you can see, there are various blocks over here, and each of these blocks has a unique ID. For first block, it is E399H. For second, it is something 0C at FBH. And for the third one, it is 0C2F for H. And below that you can see there is a function which is AFL maybe log over here. So what happens is that AFL actually maintains a coverage bitmap, which is a shared memory, and it uses this unique ID of each particular block to measure code coverage. We will be talking about that in part 2, but right now this is just for the reference. So let's move on to next slide, that is fuzzing process. As you can see, a coverage guided fuzzer requires certain seed inputs or some seed files, and it maintains a queue of them. Then it will run instrumented target with the input, and then it will check if there is any new crash or any new code path being discovered. In case input causes any crash in the target program, then fuzzer will save that crash into the crashes folder. If fuzzer finds that it is discovering a new code path, then fuzzer will queue that input to the input corpus, and same cycle will be repeated again. That way fuzzer can find new crashes or can discover new code paths. Now let's move on to another topic, that is corpus collection. Before you start fuzzing, it is always a good idea to have a good file corpus, because that will help your fuzzer in quickly discovering new paths and new crashes in short amount of time. Even the coverage guided fuzzer can discover file format at their own. It will take a lot of time. So if you provide a initial good set corpus, then that will be helpful. One of the way of collecting corpus is to look For regression test cases, if you are fuzzing some open source library or software, then they generally maintain a good corpus of all the crashes, all the test cases which they have fixed. So that will be a good start. We'll be seeing them in part 2 when we'll be fuzzing TCP dump with that. Another thing you can do is that you can use available corpus files on the internet. For example, author of EFL maintains a good file corpus for image files over here. So you can go to this URL and you can download that archive file. That will help you if you want to fuzz any image viewer, any image reader software. Similarly, you can get good media file corpus from samples.ffmpg.org. So if you go to this URL, you will get various types of video, audio files which can be used for fuzzing. You can also search GitHub and you can do Google search query that will give you various file types as well. Let's move on to another topic, corpus minimization. So it is always a good idea to have a good corpus, but is it a good idea to have like hundreds or thousands of file or having a very large file in your corpus? Certainly they are not, because for example, if your file size is say 10 MB or say 100 MB, then EFL uses a strategy called bit flip or byte flip, where it sequentially changes every bit and byte. So if your file size is more, it will take more time, it will spend more CPU cycles, and sometimes it may not be worthwhile. So if you want to fuzz, then make sure that you provide input seed corpus which contains files of small size. AFL recommends that you use input seed corpus where files are less than 1 MB. Also, if there are certain files which trigger same code path, then you need to filter them out. Otherwise, fuzzer will spend unnecessary cycle in going through same path again and again. AFL offers one utility, that is AFL cmin, which we are going to see in part 2, and it helps in removing files which causes same code path. We will say more of that in part 2. Let's move on to another topic, that is root cause analysis. Now that you found a crash after running a fuzzer, what is next? So you need to analyze why your program is crashing while processing this file. You need to figure out which field in file is causing crash, what value and that particular field is causing crash, and which condition in program is causing this crash. So this condition in program is what we call as vulnerability. Now, if you get one or two crashes, then you can easily go through them and you can easily debug each of them. But what happens when you get hundreds or thousands of crash? In that case, you need some automated tools to trace all the crash. And for that, there are various tools available like CrashWalk, eTrace, AFL Collect. So we'll be using CrashWalk in part 2 for tracing crashes. We will see how do we install it, what are the different command line options it has, and how does it can help us in tracing various crashes. Let's move on to next part and see what we have learned. We have seen what is instrumentation, we have seen what is fuzzing process, we also seen what is corpus collection and root cause analysis. With that, let's move to next part, that is reporting to vendors and bug bounty. After you have found crash, you need to do root cause analysis and you need to figure out if that particular vulnerability is exploitable or not. In case you feel that that particular vulnerability which you are working on is exploitable, then you need to report it to vendor first so that vendor can fix it and release and fix for that. Generally, vendors have an email ID something like security@vendor.com. So you can get in touch with them using that email ID or any other way which you prefer. Also, make sure you do not publicly disclose your finding until you have confirmation from the vendor that the bug has been fixed. Also, some vendor offers bug bounties when you report vulnerabilities to them, and there are various bug bounty platforms like Bugcrowd and HackerOne. If you want, you can use them. So this concludes part 1 of our training titled Fuzzing and Finding Vulnerabilities using AFL and WinAFL. We'll move to part 2 where we'll see what is AFL and how we can use it to fuzz various software on Linux. Thank you. Hello everyone, welcome to part 2 of our training titled Fuzzing and Finding Vulnerabilities using AFL and WinAFL. In part 1, we have discussed about various topics like what is a vulnerability, what are different types of vulnerabilities like integer overflow, integer underflow, out of bound read, out of bound write, etc. We also discussed what is fuzzing, what are steps involved in fuzzing, what are different types of fuzzer, and what is binary instrumentation, basic blocks, and crash tries. So let's move on to part 2. Part 2 is mostly focused on Linux and AFL. And this is our agenda for part 2. At first, we will see what is AFL, how does it works, what is fork server versus persistent mode in AFL, what are different fuzzing strategies, what are sanitizer like ASAN, UBSAN, AMSAN, and TSAN, and how does sanitizer help in finding more bugs. Then we will do some hands-on. So for that, at first, we will compile a very simple C program using AFL compiler wrappers, and then we will fuzz that program using AFL. When we fuzz that program using AFL, we will find different types of crashes. So we will use GDB and source code. We will debug the program and we will see what are the root cause for different issues. Then we will use a tool called CrashWalk to perform crash tries. We will see how do we install CrashWalk and what are the different command line options and how can it help us in tracing the different crashes. Then we will move on and we will see how do we fuzz a real life program like TCP dump or libtiff, and then we will move to the conclusion. So let's see what is AFL. In case you are wondering, full form of AFL is American Fuzzy Loop, and it has been created by Michael Zalewski, who used to work at Google Project Zero. AFL is a fuzzer with instrumentation guided genetic algorithm. It means that, as we have discussed in part 1, coverage guided fuzzer uses a technique called binary instrumentation, in which they add instrumentation code in each and every basic blocks. So when a program gets executed, they can monitor the program execution and they can see what are the different parts a program is taking, and based on that they can change their input. We will discuss more about this in later slides. AFL also comes with set of utilities like AFL fuzz, AFL cmin, AFL tmin, and AFL showmap, etc. For this training, we'll be mostly using AFL fuzz and AFL cmin. AFL can work in two modes, that is fork server and persistent mode. Fork server is the default mode for AFL. If you want to fuzz using persistent mode, then you have to make some changes in your program. In fork server mode, AFL creates the copy of the process and then it will create a clone of that. In persistent mode, AFL simply loops around the function or a particular set of code blocks. AFL mutates the file based on various strategies like bit flip, byte flip, havoc, or splice. So these are the various strategies which AFL uses to modify the content of the file to help in the fuzzing and find the vulnerabilities. We'll discuss about them in later slides. Let's move on and see how does AFL works. So AFL adds compile time instrumentation to the program which you want to fuzz. And if you want to fuzz any program, then you need to use compiler wrappers which AFL offers. AFL offers different compiler wrappers like AFL GCC if you want to compile any C program, or if you want to compile any C++ program, then you need to use AFL G++. Similarly, if you prefer to use CLang, then you can use AFL CLang and AFL CLang++. Or if you want to use LLVM, then you can use AFL CLang fast and AFL CLang fast++. AFL uses binary rewriting technique to add instrumentation at each basic block. So each basic block will have a unique random ID, which AFL will use to track the coverage of the program. In case you are wondering how does AFL tracks the coverage or the code path a program takes, it is done by assembly equivalent of the following pseudocode, as you can see it over here. AFL maintains a coverage bitmap, which is actually a shared memory. And how does it work is that it will take the compile time random of the current block. For example, let's see right now the program is executing this particular block. So it will take the compile time random or the unique ID of that block, which in this case is CBFBH. It will save it in the current location and then it will use the previous location and it will XOR it with that. So suppose if the previous location is this block, Then it will take 0E399H and it will XOR it with the 0C at FBH over here. And it will give you a value. So AFL will go to that particular offset in the bitmap and it will increase the value over there. So this value will get increased every time a block control transfer from one to another one. For example, if a block comes from first to second, then it will use the same algorithm and it will increase the value of that location. Later on in future, if again some input causes this same block, so it will again use the same XOR algorithm and it will increase the value at this particular location. After that, it will mark the previous location as current location and it will right shift it by 1. So it will mark this current location as the previous location and it will right shift this value by 1. In case you are wondering why there is a need of right shifting current location by 1, then it is because of a very simple reason. This technique helps to identify the transition between two consecutive blocks. For example, if control transfer from block A to block B and then to block C and block D, just notice the highlight part over here, C to D, while later on some input causes the program to have a transition from block A to block B and then to block D and then to block C. So if you can notice, the block is control is getting transferred from D to C over here, while in previous case it was getting transferred from C to D. So in case you don't use this right shifting mechanism over here, then you cannot identify what is the unique path over here from C to D or D to C. Since these two are the separate paths, there is no way to identify that. So what AFL will do is that it will mark the current location. In case first one, if the block is transitioning from C to D, it will take the current location, it will right shift it by 1 and then it will XOR it with the unique value of the D. So that will give some different value in than the second case. In second case, it will take the D block and it will take the unique value of that block. It will right shift it by 1 and then it will XOR with C. So these two value will be different, and in that way AFL can identify the difference between two consecutive blocks. So AFL can identify if the control is transitioning from block C to D or from block D to C. Now let's move on. Now let's see what are the different modes AFL offers. So AFL can work in two modes. First one is fork server and second one is persistent mode. In fork server mode, when you fuzz a program, what happens is that AFL will stop the execution of the program at main. Then it will use fork to create a clone of the program. And then this newly created clone process will process all the input and AFL will monitor it for any crashes or hangs. After this clone process finishes the execution, AFL will kill it. And then AFL will again use fork to create another clone of the program and same process will be repeated. Now using fork server mode can help in saving time and improve fuzzing speed, because there are certain programs which take a lot of time in initialization. This is because they might need to load different libraries or they might need to perform some operation which are time consuming. Now let's move on to another mode, that is persistent mode. So as you might have noticed, in case of fork server mode, AFL still needs to create clone of the program and then it needs to monitor that process for hangs or crashes and then it needs to kills after the operation has been finished. So that is again time consuming and there is a way to speed things up. So in persistent mode, AFL uses a concept called in-process fuzzing or in-memory fuzzing. In case you want to fuzz a program in persistent mode, then you need to write a simple harness or you need to modify your program. And as you can see in this example, you need to use a keyword like AFL loop inside a while loop. And in that case, what AFL will do is that it will continuously loop around this code block. So as soon as the control reaches to this code, AFL will start looping around and then it will fuzz the program. So this will drastically improve the performance, but it will not fuzz the entire program. So if you want to know more about fork server and persistent mode, you can go to the reference link I have given below or here. That will give you more idea of how this two mode works. Now let's move on and see what are different fuzzing strategies. So fuzzing strategies are set of strategies which AFL uses to modify the contents of the input file. And what happens when you fuzz a program using AFL? AFL reads the input file, it will modify their contents And to modify the contents, AFL uses these strategies. So let's go to each of them one by one. In case of bit flip, AFL flips the bit. It means that 1 becomes 0 and 0 becomes 1. And during the fuzzing on the AFL status screen, you will see that when it mentions a strategy, it will also mention the text something like this: 1 by 1 or 2 by 1 or 4 by 1 or 8 by 8 or 32 by 8. What does it means is that it will flips 1 bit at a distance of 1, or it will flips 2 bits at distance of 1, or it will flips 8 bit at distance of 8. So what it will do is that it will flips 8 bit, then it will move forward 8, and then it will again flips 8 bits, or it will flips 32 bits, it will move forward 8 bits, and then it will again flips 32 bits. So this will be the convention which AFL uses during the fuzzing process, and it will, same thing you will see on the AFL status screen. Now next strategy is byte flip. In byte flip, it will flips the byte, and it will uses the same strategy, like it will flip 1 byte at a distance of 1, or it will flip 2 byte at distance of 1, or it can flip 32 byte at distance of 8, etc. Then next strategy is arithmetic. So in arithmetic, AFL do some random arithmetic operation like plus, minus, addition, subtraction using random numbers. Next strategy will be havoc. So in havoc, AFL do all the random things like bit flip, byte flip, addition, subtraction, or interest, or splice, anything. So it can use any of this strategy during the havoc stage. Next is dictionary. So dictionary is very useful when you are fuzzing some complex file format which has predefined keywords like PDF or image files or media files. For example, if you are fuzzing a PDF file, then it can have different keywords like streams, or it can have header like PDF or etc. like JBig2 or whatever it uses. So if you know all the keywords which a particular file format uses, then you can provide dictionary as an input to the AFL, and AFL will use those dictionary keywords to fuzz. AFL also has capability to detect the dictionary words. It can figure out them because it's a coverage guided fuzzer, so it will monitor the program execution, and based on that it can figure out the keywords. Next strategy will be interest. So as we have seen during the discussion about the different types of vulnerability like integer overflow and integer overflow, what happens is that if the values are too high like 0ff or 07f, then that will cause program to crash. So AFL has a set of interesting values like 0ff, 07f, or 8 or 16 or 32, and AFL uses this value and it will replace the content in the file with these interesting values. Next strategy will be of splice. So in splice, AFL splits and combine 2 or more files, and it will generate a new file. In that case, AFL can split the files at any random location, and then it will combine them and it will feed the newly generated file to the input program, and it will see if it crashes or not. So these are the different strategies which AFL uses to fuzz a program, and there is no specific order in which AFL will use these strategies. So if you want to know more details on that, you can go to the GitHub URL of AFL and you can read the technical details over there. That will give you more idea. Let's move on and see sanitizers. So sanitizers are tools based on compiler instrumentation, and they are very helpful for identifying bugs. They can discover bugs like large memory allocation, heap overflow, use after free, etc. And there are different types of sanitizers like ASAN, AMSAN, UBSAN, and TSAN. So the question over here is that why do we need to use sanitizers? So if you don't use any sanitizer, then what happens is that if there is some memory corruption in your program, or if there is some undefined behavior in your program, then there are chances that the program will not immediately crash. And so in that case, sanitizer will be very helpful. Sanitizer uses different techniques, so they can identify bugs very quickly. So let's go ahead and see the different types of sanitizers now. So first one is address sanitizer, which is also called as ASAN. And if you want to compile your program with address sanitizer, then you need to use compiler directive, which is fsanitize is equal to address. So if you are compiling your program using GCC, just add this line, that is hyphen fsanitize is equal to address, and it will compile your binary with asyn. Asyn can detect various issues like use after free, heap buffer overflow, stack buffer overflow, initialization order bugs, memory leaks, and use after scope. So if you use asyn with your fuzzer, then you will get more bugs. If asyn uses various tactics like shadow memories, etc., so as soon as some corruption happens, it can immediately figure it out and it will crash the program. So that will help you in finding the vulnerabilities or bugs in your program quickly. Now let's move on and see other types of sanitizer, which is undefined behavior sanitizer, or it is also called as UBSAN. So undefined behavior sanitizer detects various undefined behavior in the program like divide by zero, integer overflow or integer underflow, and uninitialized reads. If you want to compile your program using UBSAN, then you need to use compile a directive like fsanitize is equal to undefined. And UBSAN also helps in finding new bugs, and it helps in finding bugs quickly. Let's move on and see other types of sanitizer. So there are two more sanitizer, which is memory sanitizer (MSAN) and thread sanitizer (TSAN). If you want to compile your program using MSAN or memory sanitizer, then you need to use compile a directive, which is fsanitize is equal to memory. Memory sanitizer will detect uninitialized memory reads, etc. If you want to compile your program using thread sanitizer, then you can use compile a directive, which is fsanitize is equal to thread. Thread sanitizer will mostly detect data races inside the various threads, etc. So if you want to know more details about sanitizer, you can go to the following reference link, and that will give you more details on the sanitizer. Since we don't have much time, so we will not be going in much detail on the sanitizers. Let's move on. And so what we have learned so far. So we have seen what is AFL, how does it works, how does it instrument the program, how does it check the coverage. Then we have also seen what are the different fuzzing strategies. And then we have seen the different sanitizer and how do we enable them and how do we compile our program using sanitizers. What are the different compile directory for them. Now let's move on and do some hands-on. The first thing we will do is we will see how do we compile and install AFL on our system. I hope that all the attendees have a Linux VM ready with you. I am using Kali Linux. So if you have Kali, that is better, but any Linux variant will work. So first thing you need to do is that you need to download AFL. In case you have not downloaded already, you can run this command, that is git clone, and URL https github.com google afl.git on your system, and then you need to run make. So let's go ahead and see. On my system, I have already downloaded AFL, so I just change my directory to AFL, and let's run the make command and see what happens. So as you can see, it is compiling AFL. Now another thing we need to do, if we want to enable LLVM mode, we need to go to the LLVM folder, which is cd llvm_mode, and we again need to run make command over here. So this will enable the compiler wrapper, which is AFL CLang fast and AFL CLang fast ++. So before you run this command, just make sure that you have CLang installed. If you don't have CLang installed on your system, then you can install it by running command sudo apt install CLang. In my case, I have already installed, so it should not be an issue. Now let's move back to our AFL directory and install the AFL. So for that, we will use command, that is sudo make install. As you can see, AFL has been installed on our system. Now let's move back to our fuzzing directory. I have already shared some file, which is imageread.c and imageread_par.c. So first we will fuzz imageread.c. Let's look at the source code of that. So this is our vulnerable program, which contains a lot of vulnerability. So first we will fuzz it in normal mode, that is the fork server mode, and then we will modify it and we'll fuzz it in the persistent mode. So that will give you a more idea on what are the default default mode in AFL and what are the different modes you can use. So as you can see, this vulnerable program has a structure that is image. Here there is a header of size 4 bytes, which is of type character. Then there is a variable named width, which is of type integer, and there is another variable which is height, which is also of type integer. And then there is a array, character array, which is of 10 bytes data. Now, if you look into the source code of this program, you can see that there is a main function, which is a standard C function. It expects two parameter argc, argv, and then it calls the process image function with the first parameter, that is a file name. So we need to pass a file name to this program. And let's go ahead and see what this process image function does. So it actually opens that file name, which we pass as an argument to this program. It will do some sanity checks over here, whether the file exists or not, or whether it is able to open that file or not. And then it will read some data from the file in the structure of type image. So we are basically parsing a imaginary image file over here, which our program is parsing. So it will use a while loop and it will keep reading the data, and then it will perform various operations. Like over here, it will calculate one value size 1 based on the image width and image height, and then it will allocate some memory using malloc, and then it will do some mem copy. So it will copy some data from the image to this newly allocated buffer. It will free the buffer, and as you can see that it contains a lot of vulnerability, as we have discussed in our first part, like integer overflow, heap buffer overflow, double free, use after free, etc. And out of bound read, stack out of bound read, stack out of bound write, memory leaks, etc. So let's go ahead and compile this using AFL. To compile this program, we will use AFL clang. So we need to run this command, that is AFL clang image read.c. We will use address sanitizer so that we can identify the crashes quickly. So we will use the flag fsanitize is equal to address, and we will also use fsanitize is equal to undefined. So you cannot use asan and amsan together because they are mutually exclusive, but you can use fsanitize address and fsanitize undefined together. We don't need to use thread sanitizer over here because we are not having any thread in this program. And we will also add G flag so that it will enable some debug support. And we will give output file as image read AFL. And as you can see that it's instrumented our location. It has instrumented our program at 40 location, and asan and amsan is enabled, and the current instrumentation ratio is 33%. So you can actually change this ratio using AFL flags. Now another thing you can do is you can enable AFL harden, so that will enable more stricter check and you can find more bugs. So just enable AFL harden, just give this flag and compile the program. As you can see that our compiled binary is 64-bit, and now it has instrumented at 47 location. Previously it has instrumented at 40 location. So now that our binary has been compiled, let's go ahead and fuzz this. So to fuzz that, we will need to provide it some input, and so let's create an input directory, that is make_dir input, and we need to provide it some test file, some seed corpus. So in this case we will use a very simple text string, which is echo will redirect it to a text file inside the input file, input one.img. So as you will notice that we are not giving any specifically crafted file to AFL, and AFL will be automatically able to figure out the structure of the file. So now that we have created an input seed corpus with one file, let's go ahead and fuzz it. So to fuzz AFL, you need to use command, that is AFL fuzz -i, that is for input. So you need to provide your input folder over here, then -o and output folder over here. Then we will specify memory as none because we have compiled our program using asan. So if we don't provide any memory over here, then it will give some error and it will not be able to run. And then hyphen dot slash img read AFL and @@. So why we use this @@ symbol is that at the runtime AFL will replace this symbol with the file name, with the test file name. So let's go ahead and see what happens. As you can see that it started fuzzing our program, and it started finding some crashes. So you can see that there are some unique crashes which is increasing, and you can see that AFL display a nice status screen over here. So I'll be explaining some of this. What does it means? As you can see on the right hand side, AFL display the name of the first executable, which in our case is img read AFL. Then under the process timing section, it displays various statistics like runtime. It means that since how long we have been running AFL, in this case it was 7 minutes and few seconds. Under the last new path, it display when it found last new path, that was again 7 minutes and 49 seconds before. Last unique crash, it means that when AFL found the last unique crash, that was 1 minute and 29 seconds before. And last unique hang, it means that when AFL found the hangs last time. So AFL has not found any hangs as of now. On the right hand side, you can see under overall results, cycles done, it means that the number of time AFL has processed all the input in the input queue, and it again started from the 0. So as of now, the cycles done are 14. It means at 14 times it has processed all the inputs, and it again started from the 0. Total paths will give you the total paths it has found, that is only 2 in this case. Under unique crashes, it will give the number of unique crashes it has found, which in this case is 9. So as you can see it over here under total crashes, they are around 4,000, but out of 4,000 crashes, only 9 are unique, rest all are the duplicate crashes. Then under cycle progress, you can see that it shows now processing as 1. It means that right now it is processing the test case number 2 from the input. Under pass timeout, you can see that it displays 0. So if there are certain paths which continuously result in the timeout, then AFL will display their count over here. Then under the stage progress, you can see that it displays havoc. So what does it mean is that right now AFL is using strategy named havoc. As we have discussed before, AFL can use various strategies like bit flip, byte flip, arithmetic, interesting, splice, etc. So under havoc, it can also use any of this strategy randomly. Then in stage execution, it display the number of execution it has performed for this particular stage. And under total execution, it displays the number of total execution it has performed for all the input and for all the stages. Under the execution speed, it will give the detail what is the current execution speed, that is somewhere around 30 to 40 execution per second, which is slow. Under the fudging strategy yield, it gives details on various fudging strategies which has resulted in new paths, or for example, in case of Dream, how much execution it has to perform to reduce the file size to 25%. Then on the right hand side, you see under map coverage, there is map density and count coverage. So what does it means is that how many data bitmap can hold and how many it has already utilized. Under the finding its depth path, you can see that the favorite path are 2. It means that how many paths are there which AFL thinks are its favorite. And then there are total crashes. So I will not be discussing all of them because that are not needed actually. So you can actually see total crashes which are around 4,000 something, out of which 9 are unique crashes, which we have already discussed over here. Total timeouts are here, which means that when AFL was processing test input, they did not respond in a specific amount of time. So that is what considered as a timeout. And under the path geometry, you can see that the labels, it means that the current level which AFL is processing, it can process is 2. So what happens is that when AFL process first input seed corpus, it will display level as 1, and as it started discovering new paths, it will increase the level. So right now it is at level 2. Under pending, it will display what are the paths which are pending. So it is none. Pending favorite, is it also none. own file. So as you remember, we have given only one input file, and after that it has found one more path. So that's why it is displaying total path as 2. Imported, it will be used when you are running it in a multi-core system and stability is 100%. So these are the details about the AFL status screen. If you want to know more details, you can always refer to a doc. Now that you are familiar with the fuzzing our simple program with AFL, uh, you might be knowing that when we use AFL to fuzz our simple program, it generated a couple of crashes. So now we'll proceed to our next topic, that is root cause analysis using GDB. So let's go ahead and do some root cause analysis. But before that, I wanted to show you the structure of output folder. When you fuzz a program using AFL, what does output folder contain? We will have a look at that. So as you can see it over here, the output folder contains couple of folder and files. So it will contain crashes folder, which actually saves all the crashes which AFL finds. This crashes.pec is something I have created just for the backup. Then there is a file name fuzzbitpep and there is a file name fuzzstats. So this will be used by AFL. And then there is a folder named hangs, which will store all the hangs which cause program to hang. And then there is a something called plot data file. So AFL will use that. We don't need to worry about that. And there is a queue folder. So this is the folder which contains all the inputs which are in the queue. So let's go ahead and see what the queue folder contains. You can see that it contains one file. Let's dump the content of that. So we'll use a hex editor xxt. If you don't have, then you can simply install it by typing sudo apt install xxt. Let's dump the content and see what does it contain. So as you can see that it contains img and 0a over here. So this was the input which was in the queue, which AFL will process when you run it. Now let's go ahead and see what does crashes folder contains. So you can see it over here that crashes folder contains couple of files. Now the point I wanted to make over here is that AFL follow a very good file naming convention. As you can see that it follows the file name something like id00. So this will be the ID of the file. Then sig06, it means which signal was received when a program crashed. And then the source. So source means what was the initial file which AFL mutated to generate this new file over here. And then operation. So it means the which strategy AFL used to make changes to this file. So in this case, it was operation havoc. So it means the strategy was havoc, and it was rip8, that is repetition of 8. You can similarly see the other file names like id 00001, signal again 06, source was again the same initial input file which we have given, and operation was again havoc, and it was repetition of 128 bytes over here. So let's go ahead and do root cause analysis. So we will use first file, and then we'll see what was causing the crash, what was the condition in the program, and what was the field in the file. So first we will do is that we'll verify our crash. So we'll use our executable file, that is img read. And then we will give the path to the crashing file, that is id 0. And you can see it over here. There are a couple of messages. So you can see address sanitizer message. It is a heap buffer overflow over here. And you can also see undefined behavior sanitizer message over here. So this is because there is a signed integer overflow over here. And if you see the data which contained inside the file, so the header contains bracket mmg, then some random data, then width and height both are negative. So this is what was causing the integer overflow. We'll have a look at that. So it is at line 34 in the imagery.c file. And then the heap buffer overflow is in malloc, which is somewhere around line 66 in the imagery.c file. So let's first go ahead and check the source code. What does this line contain? So remember the line, it is line 66 and line 34. So we will see the source code. That will give you a much better idea. So let's go to line 34 first, and then we will go to line 66. As you can see it over here in line 34. So as we have discussed previously, it is an integer overflow. There are two negative number, and that will actually add them up, and the size one will get truncated, and it will become 0 or a very large number. And similarly, let's go ahead and see what is at line 66 over here. So you can see over here is that there is a malloc of size 3, and size 3 is getting calculated by dividing width and height. Since width and height both are negative, we need to see what will be the value of size 3. So we can actually put a breakpoint at line 62, and then you can see there is a mem copy instruction in both the cases. So this is what causing heap overflow over here. So let's go ahead and set a breakpoint at line 34 first, because this is where the integer overflow was happening, and then we'll set a breakpoint at line 62, because this is where the value of size 3 is getting calculated. So we will use GDB, and if you don't have GDB installed on your system, you can simply install it using sudo apt install GDB. Since I already have GDB installed, let's go ahead and run. So we will give our image file name over here, that is imagery.afl, and then we need to give argument. So we'll use R. We can give the file name with the R. So as you can see, we are using the first file, that is id 000000, and this is a full file name. Let's go ahead and run this. So as you can see that our program is crashing under GDB with the provided input. Now let's go ahead and put the breakpoint at line 34 and at line 62 using command B and line number. So you can also use file name like imagery.c and colon line number, but since we are only having one file, when you put breakpoint on the line, it will will keep the breakpoint at this file name only. So let's go ahead and run and see what happens. So as you can see, our breakpoint has triggered over here, and let's step over and see what does size contain. So we'll use command P as size set E1, and as you can see that this is the value of size 1 after adding this two number. And we also see one sign integer overflow message over here by undefined behavior sanitizer. So it means that when this two number gets added, the size 1 contain a truncated output, because it cannot save that big value inside size 1. And since there was no crash, so let's continue. And you can see that our second breakpoint has been triggered. So this is where the value is getting calculated for size 3. So let's do a step and see what is the value of size 3 over here. So as you can notice, it's 0. Now let's see what does the code contain over here. So we will again do step over, and we will see that there is a malloc call which is allocating memory using size 3, but size 3 is already 0. So when you pass 0 to malloc, it will not allocate any memory. And since there was no check if malloc is successful or not, there is a mem copy call over here which is copying some data to buffer 4, which is not allocated, and there is some data inside the image.data. So it will crash over here. So if you do a step over or again over here, you can see that SN triggers a crash over here. So this is a heap buffer overflow because there is no memory which is allocated, and program was trying to copy some data over here to unallocated memory. So this was the root cause of the first issue, where the memory was not getting allocated and program was trying to copy some data. Now that we have looked at one issue, let's take one more. So we will again try the second crash file. Let's try with the 1 this time, and you can see that it is again a heap buffer overflow over here. So it is, I think, on the same line, so we'll skip that. Let's see, I did 2 if we find any interesting test cases. Okay, you can see over here. So input 2 actually triggers a stack overflow, and there is out of bound read or maybe a write over here at line 70 and line 75. So first let's go ahead and see what does the code content at line 70. So let's again open our source code, that is img read.c, and we will go at line 70 and 75. We'll see what does it contains. So let's go ahead and see at line 70. So you can see that at line 70 there is a array that is of size 10. You can see it over here. Buffer3 is of size 10. It is of type character, and since there is out of bound read over here, it means that size 3 will contains the value which is more than 10. And similarly, let's go ahead and see what does size what is at the line 75 over here. So you can see over here is that there's a buffer3 where programs try to write some data, some character C at this location. So this is actually an out of bound write, because program is trying to write some data, while previously over here the program was trying to read the data at this offset. So this was out of bound read, and this is an out of bound write over here. Now let's go ahead and see how does this look like in the GDB. So we will again run GDB, and let me first copy the file name over here. So let's run GDB and see how does it look like. Image read AFL R. We will copy our file name. We'll paste it over here, and as you can see, the program again crashed over here. So what we can do is we can set a breakpoint at line 75, and we can run it. So we need to print the value of size 3, because this is where out of bound error was coming. So let's print size 3, and as you can see, it contains a very large value, and the size of buffer is only 3 bytes. Oh, sorry, the size of buffer 3 is only 10 bytes. So the maximum value which buffer 3 can hold is 10 characters only. But when program tries to write some character at offset 39218, which is beyond the size of this buffer 3, it will cause out of bound write error over here. So this was the root cause in the second case, where the index value was so big that it was out of bound for the buffer, and that was causing the program to crash over here. So if you do a step in, program will crash over here, as we can see. And so this was the root cause. So this is how you figure out the root cause. Now that you know how to use AFL to fuzz a simple C program and how to do root cause analysis using GDB, let's move on to next topic, that is crash triage. So to start with, why do we need to do crash triage? This is because when you run a fuzzer, when you fuzz a real world software, you will get hundreds or thousands of crashes, and it will not be possible for any individual to manually analyze those crashes, because it will take a lot of time. And so we need some kind of tool which can help to automate this crash analysis task. There are a lot of tools available, but for this training, we will use a tool called CrashWalk. CrashWalk is a tool which is written in Go language. So if you want to install CrashWalk, you need to install Golang first, and then you can install CrashWalk. It is also dependent on one GDB plugin that is called exploitable, and it expects that plugin at a specific path, that is your home directory, source folder, exploitable, and then inside that exploitable.py. So let's do some hands-on. We will install CrashWalk first, and then we will use it to triage the crashes. First thing we need to make sure is that we have Golang installed on our system. So if you are following me along, please type this command, that is sudo apt install Golang. It will install Golang on your system, and after you have installed Golang, let's go ahead and install Crashwalk. So to install Crashwalk, you can simply use this command, that is go get-u github.com/bngy/crashwalk/cmd ... What this command will do is that it will download the Crashwalk and it will install it under your home directory in Go bin folder. So let's go ahead and see the files. Crashwalk has three executable files, which is cwdump, cwfind, and cwtrash. So in this training, we will use cwtrash and cwdump. Cwtrash is the binary or executable which will do the crash trash, and it will create a database named crashwalk.db. What it does is that it will take each and every input file which it finds, it will feed that to the program, and it will monitor it for any crashes. If the program crashes, it will save the details like call stack and hash, etc. to the database, and then we can use another utility, that is cwdump, to search, or we can use cwfind to search and find the data from the database for a particular crash. So now that we have installed Crashwalk, we need to install exploitable plugin as well. And since it expects it at a particular folder, that is your home directory and source, let's go over there. So first thing we will do is we will go to the home directory and we will create a folder named src, that is source. Since I have already created it, let's go to that. If you have not created, simply create a directory named source. Inside the source directory, you can simply run git clone command. So you can run this command over here, that is git clone https github.com jfoot/exploitable.git. So I have already cloned this on my system. Now let's go ahead and see. As you can see, there is a script called exploitable.py inside this directory. So Crashwalk should work now. Now we will go to our AFL folder, our fuzzing folder, where does output folder resides, which contains all the crashes. So as you can see, all the crashes are inside output folder. And now we will use Crashwalk tool to try these crashes. So what Crashwalk will do is that it will filter out all these crashes. If there is any duplicate, it will filter them out. It will generate a report and it will store in the database. So let's go ahead and let's see what are the command line option cwtrash has. So as you can see, it offers one AFL mode. So if you want to try any AFL crash, then you simply need to specify -AFL and then you have to specify root directory, and that's it. It will actually go to the output folder. It will go to the crashes folder. It will read the readme.txt file, as we can see it over here. And it will extract the command line parameter and name of the executable and memory limit, etc. from this file, and it will use that to replicate the crashes. So this is going to be command line option for cwtrash. The command is cwtrash-afl, which means that it will use AFL mode. Then we will give -root. It means that the directory which it will search for the crashes. So the command is very simple. Let's go ahead and run it now and see what happens. As you can see, some of the crashes are not getting replicated. You can see a message no crash detected like this, while few of the crashes are getting replicated over here. So the reason not all the crashes are getting replicated here is that we have not provided async option over here. Since we have compiled our sample binary with address sanitizer, we need to explicitly give this option for it to work. So now let's go ahead and run it again by giving async options and see if it is able to replicate the crashes or not. So async options are straightforward. As you can see over here, you need to give the command like async underscore options is equal to abort on error, that is 1, symbolize is equal to 0, followed by your cw tries command. And since we have already run it for the one time, what it will do is that next time we run cw tries, it will skip all the crash file which it has already analyzed. So what we need to do over here is that we need to add scene option. What this option means is that cw tries will again use the file which it has previously checked. So let's go ahead and see what happens this time now. I have given wrong option, sorry. Okay. As you can see, the crashes are getting replicated now. And so far we have not received does not crash message over here. So now what cw tries will do, it generates a lot of crash summary details like file name, their hash, their classification, hash of call stack, the command which it has used to replicate the crash, that is image read AFL output and crash file path, and then it will have some disassembly, it will have some register value over here, and it will give some extra data like description, that is abort signal, then explanation, etc. So this data will be saved in a file called crashwalk.db. Over here, as you can see, this is the database which saves all this crash info. And then you can use another utility which comes with crashwalk, that is cwdump, to dump the info from crashwalk.db. So the command is straightforward, just type cwdump and crashwalk.db. So it will dump all the data which is inside the database. You can either use more option, or you can redirect this output to a crash a text file like crashes.txt, and you can go through that file using vi, and you can browse it. As you can see, it has filtered out duplicate crashes, 1 of 6. So it means that there are 6 files which are causing same crash. So it will only use one of this file, rest it will discard. Similarly, you can see there are 1 of 3. It means that there are 3 files with the same crash, but it will only store one details for only one file. And so this is very helpful when you want to do automated crash triaging. Again, you can see the description over here, access violation on source operand, there is source access violation, and it gives explanation. So this data came from GDB exploitable plugin. If you don't install GDB exploitable plugin, then in that case you will not get these details. It also gives classification like this, probably not exploitable. So if you want, you can further analyze that. Now what we are going to do over here is that we will simply copy one command, say this one, and we will see what happens. So let's just go ahead and try to replicate this crash, and you can see that the crash is getting replicated over here. So this is how you use crashwalk for crash triaging. Since in our case we had a very few files, very limited sets of files, but in real life when you fuzz a program, you might get hundreds or thousands of crashes. In that way, you can use cw tries. Cw tries has one more option where you can actually keep it running, and it will check for new crashes or a given time interval. So if you want, you can specify an option that is every and maybe say every 600 seconds or maybe every 6000 seconds, whatever works for you. So what you can do is you can simply run a screen window on your system and you can have CW tries run every hour or every few hours, and so that it can automate all the crash triaging process for you. Now that we have seen how do we install CrashWalk and how do we use it to do crash triage, let's move on. So what we have learned so far, we have seen how do we first simple C program using AFL on Linux. We have also seen how do we do root cause analysis using GDB, how do we do some basic debugging, and then we have also seen how do we install CrashWalk and how do we do crash triaging. With this, let's move to next topic, that is fuzzing open source softwares. And in this part, we are going to first two software. First one is TCP-dump and second one is libtiff. So let's go ahead and see how do we first TCP-dump. First thing you need to do is get the source code of TCP-dump and libpkp, because TCP-dump is dependent on libpkp. So you have to install both, otherwise you will not be able to compile TCP-dump. So if you have not copied the source code of TCP-dump and libpkp on your system, you can simply run this command, that is git clone, and then you can compile it and you can get some corpus and then you can fuzz it. So let's move on to the hands-on now. Let's first do a git clone so that we get the TCP-dump source code if we don't already have it on our system. So in my system, I already have TCP-dump source code. Now what you need to do after you get the source code of TCP-dump, you need to go to that TCP-dump folder and then you need to get source code of libpkp. So you can again run the command, that is git clone and URL for libpkp. Make sure that you install or you clone this libpkp inside the TCP-dump folder. And then now we need to compile libpkp first. So we'll go to the libpkp folder and then we will use configure. So this is the configure command. I will explain you first and then we will run it. As you can see, it contains cc is equal to AFL GCC. So what does it means is that I'm using C compiler as AFL GCC. Then there are some C flags. So these are the some options like -g f sanitize is equal to address. It means that we are using asyn for this compiled binaries. Then f no omit frame pointer. This will help in asyn. And then there are some linker flags. So these are same as C flags. And then we are running configure command. So let's go ahead and run the configure command. It may take some time, so we need to wait. So you may face some issue where some libraries were not installed. In case you face some issue, just make sure that you install libraries. In this case, generally you need to install flaglib and bison. So you can install both of these lib by using this command, that is sudo apt install flags, and it will install the required flaglib. In this case, I have already installed it. In case you face any issue, just run this command, and you can also install bison. So you can run this command. In my case, I have already installed it. So just in case you get any missing library or any missing dependency here, just make sure that you install all the libraries. Now that our configure command has been successful, we can simply do make, so it can compile the program. And as you can see that it has compiled our program. Let's do it again, because in my case I already have it compiled. So now as you can see it over here, it is instrumenting the file It is giving some message like 64-bit binary than SN or MSN mode, and instrumentation ratio is 33%. This may take some time to build. I hope that you are following me along and you are trying all these commands on your system. As you can see, the compilation has been successful. So now we can install it by simply typing sudo make install. What this command will do is that it will install all the libraries libpkm on the system. So let's run it. Okay, it has been successful. Now let's move back to previous folder, that is tcpdump folder, and again we need to follow the same steps which we follow to install libpkm on the system. So first we will do the configure, and for configure you can use the same command. There is no change at all. That is cc is equal to afl gcc, cflex is equal to g, f syntax is equal to address, f no omit frame pointer, then there are some linker flags, and then configure. So this command is same as libpkm, so we don't need to change anything, just run it and let's wait. This may again take few seconds or a minute. Now let's go ahead and do a make. So you just need to type make command, and as you can see you are getting some message. We are getting some messages like instrumented and same message which generally comes when you compile a program using AFL over here. So this may again take few seconds or a minute. You need to wait, and after make we will simply do make install. So that will install tcpdump on our system. Now if you want you can skip that step, because when you compile the tcpdump you will get the binary in current directory, so you can simply fuzz it from there. There is no need to do make install in case of tcpdump. As you can see that tcpdump has been compiled on the system, and if you do a ls you can actually see tcpdump binary on this directory. So now that we have compiled tcpdump, we can skip the installation part because we can simply run tcpdump from this location. And now next step, we need some test corpus. So for that what you can do is that you can go to the test folder which comes in tcpdump source code, and when you check that folder you can see that it contains a lot of pkf files. Now this is the test corpus which you can use to fuzz. This will be a very good seed corpus, and it contains a lot of files. So if you see some of these files, they contain them like heap overflow or asn or out of bound read, like that. So it means that these pkfs are for some vulnerabilities which have already been fixed in tcpdump source code, and so you can actually go ahead and use that for your fuzzing. But we need to minimize this corpus because there are a lot of files as of now. So it may be possible that some of this file may be triggering duplicate code paths which are actually not needed for our fuzzing. So we will use the utility called aflcmin and we will minimize this corpus. So let's go ahead and use aflcmin. Before that I will just remove one directory, and the command for aflcmin is simple, that is afl cmin I, that is for input. So input will give us stats which contains all the test files, and output we can say minimize tests, and m we will give as none. So m is for memory, and you can specify memory limit, but since we are using 64-bit mode, our binary is compiled with asn, and what happens is that asn will take a lot of memory. It will require a lot of memory on 64-bit system. So AFL will complain that it cannot run under 64-bit system with asn enabled binaries. So you need to specify m is equal to none. It means that there is no limit. The program AFL should not limit memory for this program. And then --/ ./tcpdump, and then tcpdump expects some command line arguments. So we will specify EE, VB, and NNR. act symbols. So this EE and VV and NN means that there are some headers which they will display in verbose mode, and R means read from the file. So let's go ahead and run this command and let's see what happens. So as you can see, there are around 1236 files, and let's see after minimization how many files we get. So this is going to take some time. You need to be patient. You need to wait for some time. Let's wait for some more time and let's see how many files we get after minimization. So as you can see, initial file corpus was of around 1236 files, which after running AFL cmin, it has narrowed it down to only 421 files. So that is 1/3 of total file corpus. That is good. Now that we have a minimized file corpus, next thing we will do is that we will go ahead and fuzz the program. So we will use AFL fuzz I input file, that is min tastes, and out, that is first TCP dump, m will be none, hyphen TCP dump EEVV NNR act, and let's see what happens now. So for me it took some minutes to minimize file corpus, but that should be fine since we have a lot of files. So we need to wait for a few minutes. As you can see, now AFL is performing dry run. So let's wait. We have around 421 files. So yeah, AFL will start fuzzing now. As you can see, current execution speed is somewhere around 35 to 40 execution per second. That is slow. And stage or strategy currently which it is using is trim. So it is trimming down the files. It is reducing their size. And total execution, as you can see, are somewhere around 3700, 3800. And let's wait for some more time. So let's see if it finds some new paths. Okay, as you can see, it started finding new paths. So right now there are around 422 paths. It has discovered around 3-4. It started discovering more paths now. So that is good. And I'm going to cancel it now. So the idea behind this was just to give you an idea. How do we use AFL to first TCP dump? What are the steps involved? What is the process? How can you use AFL cmin to minimize the corpus? And now if you want, you can go ahead and you can first TCP dump at your own. Another thing I wanted to talk about is AFL offers multi-core support. So you can run multiple instances of AFL on your system. If you have multiple CPU cores which are lying idle, then you can utilize them. So for that, you can use a utility called AFL got CPU that will give you the details on how many CPU core you have. So in my case, I only have one core, but in case if you have multiple core, it will give you the details like 4 core, 8 core, or 16 or 32, whatever you have. So you can run different instances of AFL, but it is necessary that you run one master and then you run n number of slaves. So if you want to run AFL in that mode, master and slave mode, then you need to make some changes. So for that, if you want to run master instance, then you need to add hyphen m, and you can add you can give any name over here, that is say master. Do not get confused by this small m. This small m is for defining memory limits, while this capital M is defining the master instance. And you can simply run that. Similarly, after running master's instance, you can run slave. So for that, you need to use option that is -s, and you can give some name, something like slave 1, and you can run it. So what you can do is you can run different screen sessions and you can run this command over there, and then you can run crashwalk and you can configure crashwalk to run it every few hours. So as soon as it finds any new crashes, you can get the details of that. One thing to notice over here is that when you use master and slave mode, you need to keep your output folder same for all the master and all the slaves. For example, in our case, we have given output folder name is first TCP dump. So this will be same if you want to use master or if you want to use slave. In case I want to run master instance, then I will use -m, capital M, and then I will use the name that is master, and I will keep my output folder or output directory same, which is first TCP dump. And similarly, when I run any slave instance, then I will use -s and name of the slave, let's say slave 1, and I will keep the output folder same. So what happens is that AFL will go to this directory and it will sync up. So if master found some new path, it will sync up with all the slaves, and if slave found some new paths, it will sync up with masters and other slaves. So that will actually help in quickly finding new crashes or new code paths. So you can try that out. And let's move on to another part now. That is, how do we first libdiff using AFL? So first thing we need to do is that we need to go to the libdiff folder, and then we need to run /autogen.sh command, because libdiff uses autogen. So this will generate configure file for libdiff, and then we can configure it and compile it using AFL. So as you can see, it has generated configure file now. And next step we will do is that we will run configure command over here. So you can see that the configure command is same as what we have used for TCP dump, except one extra option over here, which is CXX. And what does it means is that that we are changing C++ compiler to AFL G++, and C compiler is AFL GCC. And then you can see that we have added C flags, that is same as what we have used in TCP dump, that is G, F sanitize address, F no omit frame pointer. And then we have also added CXX flag, that is again same as C flags, that is G, F sanitize address, F no omit frame pointer. And then there are LD flags, that is linker flags over here. And then we'll be giving as a /configure. If you want, you can also add F sanitize is equal to undefined, so that will enable UBSAN for libdiff. Let's go ahead and see if our configure command is successful or not. So you can see that there are something like AFLCC message are coming over here, AFLG++. So we need to wait for some time. Okay, so the configuration command has been successful, and now let's go ahead and do a make. So we just need to type make command. Hopefully the people who are following me can type this command. And as you can see that it is instrumenting the binaries over here using AFL compiler. This will take some time. So the compilation took some time, but finally it has been finished. And now what we can do is we can type make install, so that it will install all the tools. And as you can see that it has installed a couple of tools. So the tool which we are going to fuzz over here is diffdump, that is diffdump. And what this tool does is that it displays the information from the diff file, And to fuzz this, we will need some corpus. We will need collection of TIFF file, which we can use as initial seed files. So for that, what we can do is that we can go to the URL which is maintained by author of AFL. The URL is this. And as you can see it over here, there are a lot of file format for which the corpus is already available. So what you can do is that you can click on this link, that is downloadable archive, and you can download this archive and you can unzip it on your system. So when you unzip it on your system, you will see that it contains a directory named TIFF, and which contains another directory full and images. So inside that it has a lot of TIFF file which will be using it to fuzz. First thing we need to do is that we need to minimize the file corpus. So for that we will use AFL cmin. So let's go ahead and use AFL cmin, and we will give input file as our TIFF file corpus, that is TIFF full images, and we will give output file as min TIFF dump, and we will give am as none because we compile it using asn, and so we should not be giving any memory limit, otherwise it will not work. And we will write TIFF dump @ and let's see. So as you can see, there are total of around 6,399 files. Let's see after minimization how much files we get. So we need to wait for some time. So as you can see that after using AFL cmin, it has narrowed it down to only 214 files. So now let's go ahead and first TIFF dump. So for that we will use the same command, that is AFL fuzz I, that is min TIFF dump. Output is out TIFF dump, and am is none because we have compiled it using asn and it says 64-bit binary, so it won't work if we don't set am is equal to none because asn needs a lot of memory. And let's fuzz it TIFF dump @ and let's see what happens. So as you can see, it is performing dry run. Now let's see what happens after that. It will take some time. Okay, so it will start fuzzing now, and as you can see, the total paths as of now are only 215, and right now it is using arithmetic bit flip havoc different strategies over here. And let's wait for some time and see if it discovers new paths or not. Okay, so as you can see, it started discovering new paths, and right now it is processing around 12th test case, and there are around pending 213 paths. It is at level 2. It means that it has discovered some paths at its own. It has discovered actually 3 paths, and the speed which we are getting right now is somewhere around 20 to 25 execution per second, which is actually slow, but this may be because of my VM. So I hope that this training has given you a good idea on how do we fuzz software on Linux using AFL. And I'm going to cancel it now. We'll move to the next part. Now let's go ahead and see how do we use persistent mode in AFL. So if you want to use persistent mode in AFL, in that case you need to use compiler is AFL clang fast. You cannot use AFL GCC or you cannot use AFL clang because for persistent mode AFL uses LLVM mode instrumentation and this two compiler doesn't support that. So in that case you need to use AFL clang fast. Now what we are going to do over here is that we will use our image file reader, the sample C program which we have used in the past to fuzz, and we'll modify it for the persistent mode. And then we will see when we fuzz it using AFL what kind of speed we are getting. So first let's go ahead and open the source code of that. So I have already made some changes over there. The changes are not very big, it's very minimal changes. As you can see in this code, I have simply added one while loop and I have added one keyword, that is AFL loop, and then I have entered a value as 1000, and then I have moved all the code, all the file processing code inside this while loop, and then I have closed the loop. So this is the only change I have made over here. All the processing code I have kept inside a while loop, and that's it. Now since our program is very small, so we may not be able to observe much of a performance benefits over here. But in future, if you want to fuzz any complex software, any big software, then you can use this tactic if you know that you want to fuzz any part of that software and not the entire software. So you can notice the performance benefits over here. Now let's go ahead and compile our program. So for compiling that program, we will use AFL clang fast as we have discussed, and then we will give fsanitize is equal to address, and then fsanitize is equal to undefined, and then we will give our C source code file name, and then output file name, that is image read AFL underscore per. So let's compile. As you can see that it has instrumented at 79 location, and what we can do is we can also add AFL harden is equal to 1, so it will add more checks. And yeah, I think it did not have much effect over here. So anyway, now let's go ahead and fuzz it. So before we fuzz, we need to provide a input file. So let's generate an input file using in a new directory, that is in per. So we will simply do echo img. We will redirect it to in per and one dot image file. So we have a seed file over here which contains img tag, and now let's fuzz it. So we'll use a file fuzz I in per and out. So we'll give as out per, and am is none over here, hyphen dot slash image read underscore per, sorry, image read AFL underscore per at the rate, and let's fuzz it and let's see what happens. So you can see that we are getting a speed somewhere around 300 or 200, which is helpful, and it has already found around 7 unique crashes. So let's wait for some more time and see what happens. So if you have a high-end system, you will be getting more speed than this. As you can see, the speed is increasing. We'll wait for some more time and then we will close this. So you can see that there is some performance improvement compared to a non-persistent mode over here. We are on an average, we are getting around 300 or 250 something speed, which is good. So I'm going to cancel it now, and let's move on to the next part. Now let's go to the last part, that is conclusion for part 2. As we have learned that fuzzing on Linux with AFL is very simple because source code is available for most of the softwares and libraries, and also AFL offers various compiler wrappers like AFL CLang or AFL GCC or AFL CLang fast, which you can use for the compile time instrumentation. So one other thing which you can do is that you can use SN, AMSN, UBSN or TSN, all kind of sanitizer that will greatly enhance your bug finding capabilities. If you don't use it without fuzzer, chances are that you will not find much bug. So always remember to use all the sanitizer. Then you always need to do corpus minimization. Make sure you have a good corpus at the start, and then you might face some issues like sometime you need to spend some effort in the compilation. When you try to fuzz the open source software, they are dependent on various libraries, and sometimes you face issues because of missing libraries. Some libraries are not installed, or there are some compatibility issues which you need to spend some time in solving them. But overall it was worth learning. So I hope that you enjoyed this part 2 of our training, and we'll move to the next part, that is part 3. Thank you. Hello everyone, welcome to part 3 of our training titled Fuzzing and Finding Vulnerabilities Using AFL and WinAFL. In part 1 and 2, we have covered various topics like what is a vulnerability, what are different types of vulnerability, what is fuzzing, what are steps involved in fuzzing, what is crash tries, and root cause analysis. We have also covered AFL, what is AFL, how does it works, and how do we fuzz simple software, as well as some real world software like TCP-dump and libdiff on Linux using AFL. Let's move on to part 3. This is going to be our agenda for part 3. In part 3, we'll be mostly focusing on Windows and WinAFL. At first, we will see what is WinAFL, how does it works, how does it instrument a program using DynamoRio. Then we will see what are the different types of fuzzing strategies, and then we will move to hands-on. In hands-on, at first, we will see how do we compile sample C program using Visual Studio. This is the same program which we used in part 2, which contain lot of vulnerabilities. In case you don't have Visual Studio installed on your system, you can use precompiled binary. But if you have Visual Studio, then you can debug this code later on, so that will be helpful. After that, we will move on and we will see how do we use WinDBG to find offset of first function in the simple C program which we have compiled. After that, we will see how do we run WinAFL in debug mode to make sure that everything is working fine. And then we will fuzz this program using WinAFL. So when we fuzz this program using WinAFL, it will generate few crashes. So we will use WinDBG to analyze those crashes and to find root cause. We can also use Visual Studio to debug the source code with the crashing input to see what are the conditions in the program which was causing the crash, and how does a vulnerability looks like at the source code level as well as at the debugger level. After that, we will see how do we fuzz some real world programs. So for that, I have a very simple exercise. First, we will write a simple harness or a test program to read and parse MDB file. And then we will analyze the structure of MDB file. And then we will fuzz MDB files, the sample harness test program which we have written using WinAFL. After that, I will give some details on CVE 2018-8423 and CVE 2019-0576. What was their root cause and how we found that vulnerability. And after that, we will move to conclusion. So let's move on. As we have seen in part 2, if the source code of a software is available, then it's very easy to fuzz that program because we can add compile time instrumentation and then we can check for coverage. But in case of Windows, there is no source code which is available. What we have is only DLL and exe. So we cannot add any instrumentation code at the runtime. And for that, we need a way to instrument the code. So WinAFL is actually a Windows port of AFL, and it is maintained by Ivan Frederick, who works at Google Project Zero. WinAFL uses Dynamo Rio for runtime instrumentation and code coverage. And as we have seen in part 2, there is a main fuzzing process, that is AFL fuzz. So in case of Windows, it is AFL fuzz.exe. For Windows, there is another file that is called winafl.dll, and this is the file which actually works as a client for Dynamo Rio executable, that is drrun.exe. So what happens is that drrun.exe provides some callbacks, and WinAFL uses those callbacks to trace the coverage of the program. In case of Linux, it was very easy to fuzz a program because the source code was available. So when you compile that program using AFL compiler wrappers like AFL GCC or AFL CLang, then they can easily add instrumentation code at the compile time. But in case of Windows, since it is a collection of DLL and exe files, it is not possible to perform runtime instrumentation for each and every file, because that will be too much performance intensive and it will waste unnecessary CPU cycles. Also, to perform runtime instrumentation, WinAFL will require a lot of memory, which in some cases will not be possible, as it can also affect the speed. So WinAFL uses a concept called in-process fuzzing or in-memory fuzzing, in which we need to write a sample program called harness, and that sample program is nothing but a simple C program or C++ program which calls a function from the DLLs which you want to fuzz. For example, if you want to fuzz an image file, and if you know that the parsing code resides in DLL like gdi32.dll or gdi+.dll, then you need to write a simple C program which imports this DLL and call the function which processes the files. This is something what we call as harness. For WinAFL to work, the harness program should have a function which opens the file and perform all the processing. This processing can involve calling function from other DLLs and passing input to them. This is known as a fuzz function. A very simple fuzz function is shown on the right hand side over here. As you can see, this function expects a single parameter, that is file name, and later on in the code it uses open database call to open that file, and after that it simply closes that file. So the way WinAFL works is that it will modify the input, it will modify the content of the file, and it will pass it as an argument to this function. Then when this function opens that particular file, then if there is any vulnerability, then this program will crash. So WinAFL will save this input in the crashes folder. If it doesn't crash, then WinAFL will move on and it will again modify the file, and then it will again repeat the same process. In next slides, we will see how does WinAFL process this fuzz function using Dynamo Rio. In case you want to fuzz any other file format like bitmap or EMF or WMF or any other file, then you need to write a simple C program which contains a very simple function, something like this, and that function is responsible for processing the file. In case you want to fuzz files like gdi32.dll or gdi+.dll, then you need to make sure that you call export functions from this DLL inside your fuzz function, and then you need to give this file name as coverage module name to the WinAFL. So WinAFL will instrument these files and then it will modify your input accordingly. If WinAFL finds that a particular input causes a crash inside any of this DLL, then it will save those input in the crashes folder, else it will move on and it will again repeat the same cycle. Now let's move on and see how does runtime instrumentation works on Windows. On Windows, aflfuzz.exe is the process which is responsible for fuzzing. This is same as on Linux. But in Windows, there is one more file that is called winafl.dll, and this is actually a client DLL which handles all the instrumentation from Dynamo Rio, as well as it handles pre-fuzz and post-fuzz handlers. In case you are wondering what is pre-fuzz and post-fuzz handlers, this is very straightforward. When you fuzz a program using WinAFL, you need to give offset of the function which you want to fuzz, or you need to give name of that function. So how does WinAFL work is that before it calls that first function, it will save the state of the system and then it will let that first function process the input. If first function crashes or hangs, it will save crashing input inside the crashes folder or input which is causing hangs inside hangs folder. If input doesn't cause any crash or hangs, then it will let the function finish its execution and then it will call post-fuzz handler. Post-fuzz handler will restore the state of the system and same cycle will be repeated. So WinAFL will do this for number of iteration which is configurable. This is something which can be given at a command line. Now let's move on to the next slide and see different fuzzing strategies. So if you remember these fuzzing strategies we have seen in part 2 as well, they are same. Just for a quick refresher, what bit flip will do is that it will flip a bit. That means 1 becomes 0 and 0 becomes 1. And if you see on AFL or WinAFL status screen, you will see that they will display like this. That is 1 by 1, 2 by 1, 8 by 8, 32 by 8, etc. What does it means is that it will flip 1 bit, it will move forward 1 bit, then again it will flip 1 bit, or it will flip 8 bits, it will move forward 8 bits, and again it will flip 8 bits. Similarly, byte flip will flip a byte and it will follow same notation as you can see over here. Similarly, in arithmetic, it will do random arithmetic, like it will perform some addition or subtraction of random values. And in havoc strategy, it will use any of this strategy randomly. So it can select any of this like byte flip or arithmetic or interest or splice or dictionary, and it will mutate the file. Similarly, in dictionary, if you know the keyword which a particular file format uses, then you can give a list of that, or WinAFL can automatically discover few tokens. Then there is another strategy, that is interest. So interest means it will replace content in the original file with some interesting values like 0ff or 07f or 0ffffff or maybe 07ffffff or anything which is interesting. And in splice it will split and combine two files. So since we have already covered this in part 2, I'm not going to spend much time on that. We will move on and we will see what we have learned so far. So we have seen what is WinAFL, how does it works, what is DynamoRio, how does WinAFL uses DynamoRio for runtime instrumentation, and what are different fuzzing strategies. Now let's move on and do some hands-on. So first thing we are going to do is that we are going to compile our vulnerable C program which we have used in part 2. So we will compile it using Visual Studio and I will walk you through some of that code. And in case you don't have Visual Studio installed on your system, you can use pre-compiled binary and you can follow me along. And after that, we will enable page heap for the compiled binary. And after that, we will see how do we use WinDBG to find the offset of the process image function, that is the offset of first function. And then we will see how do we run WinAFL in debug mode to make sure that it is working properly and it can fuzz our program. So let's move on to hands-on now. As you can see, we have our vulnerable program opened here in Visual Studio. And this is the same program which we have used in part 2. This is something which we have fuzzed using AFL, and it contained a lot of vulnerable code. So I will quickly walk you through that once again. As you can see that there is a structure and it contains various variable like header, which is of 4 bytes and it is of type character. Then there is a width and height, which is of type integer. And there is again a character variable that is actually an array of 10 bytes, that is data. And then there is a function. So if you go to the main function, it expects two standard parameters, argc, argv. and then it calls process image function with the first parameter, that is the name of the image file which you pass to that. And what this process image function does over here is that it will open that file, and then it will read that file data into the structure, that is this one, image structure. And then there are some operations like addition or multiplication or subtraction or malloc something, which it does after reading the values from the file. Based on those values, it will do some malloc, it will do some operations, and this is where you can find a lot of vulnerabilities. So now let's go ahead and compile this program, so it should be straightforward. And next we will see how do we use WinDBG to find the offset of our first function. So in this case, our first function will be process image function, because this is the function which takes input as a file name and then it processes that file. So we will give offset of this function to the WinAFL, and what WinAFL will do is that it will as soon as it reaches over here, it will call prefuzz handler that will save the state of the system. It will let this function process this file, and then it will wait it for finish or if there is any hangs or crash. And as soon as this function returns, it will call postfuzz handler, and that postfuzz handler will restore the state of the system, and then WinFL will again jump to the start of this function and it will change the input, and then the same cycle will get repeated. So this can be done for n number of times. This is called fuzz iteration, and this is something we can specify in the command line argument. So now let's go ahead and compile that, and next we will use WinDBG to find the offset of this function in the binary, because in real life you won't get source code, you will have binary. So I thought it is a good idea to use WinDBG rather than directly printing the offset of this function, and we'll be fuzzing the binary using WinAFL as well. Now let's go ahead and see how do we find offset of the first function using WinDBG. So I have shared a prerequisite doc. I hope that you have followed that doc and you have downloaded WinAFL and DynamoRio and copied it on your system. So I have recommended that you copy it inside your C drive and create a folder named fuzzing inside that. So I have shared pre-compiled binaries as well for our vulnerable C program. So if you have Visual Studio, that is good, you can compile that binary. If not, then you can simply use this pre-compiled binary. Also for WinDBG, you need to install debugging tools for Windows. If you don't have it installed, simply download it and install it. That will install WinDBG as well as gflags on your system, which will use to enable pagehip. So first thing, let's open WinDBG, and when you open WinDBG, you need to go to file, and then you need to open that particular file, which in our case is C fuzzing windows and readfile.exe. And when you open that, you can simply type the command, that is x, and your executable file name, that is readfile exclamation mark and name of the function for which you want to find the offset. So here it is, and you can see it over here that as you can see that when you do x readfile exclamation mark process image, it gives you this output. So this is what the offset is, and this is actually the address of the function. And since our base address is this, so this is where this file gets loaded. What we need is the relative virtual offset, and for that we need to subtract base address from this offset of the function. So that will give you the relative virtual offset, which in this case will be 10A0. As you can see it over here, when you subtract 140000 from 1410A0, you will get 10A0. So this is the offset of the first function, which we'll be using in fuzzing it with WinAFL. So what will happen is that when you specify this offset, WinAFL will come to this address, then it will call pre-fuzz handler, and it will let this function execute. And when this function processes the input, it will again call postfuzz handler, and that will actually restore the state. So this cycle will be repeated. Now let's see how do we enable pagehip for a particular binary. So as we have seen on Linux, we have various options like ASAN or AMSAN, different kind of sanitizer. So same thing you can use on Windows, that is called PageHip. And what PageHip will do is it will add some extra chat to your program, and it will help to find bugs quickly. Generally what happens in case of memory corruption, your program doesn't crashes immediately. So PageHip will make sure that your program immediately crashes as soon as it finds any error. So that will be very helpful. And to enable PageHip, what you need to do is that you need to go to the folder where you have installed WinDBG, and you need to look for a executable file name called gflex.exe. So gflex.exe is what we'll be using to enable PageHip. It has a very simple and straightforward command. So first thing you need to do is you need to run the command from administrative account as an administrator. And once you run that, you can simply type this command. That is, either you can give full path of gflex.exe, or you can add this to your environment path. So in my case, I'm giving full path, that is C program files x86 Windows kits and 10 debuggers x86 gflex.exe. Then you need to type /p and /enable, and then you need to give name of the file. So that is in our case readfile.exe, and simply press enter. So as you can see over here is that PageHip has been enabled. If you want to verify, you can again run this command, and remember this command, that is gflex.exe /p. When you press enter, you can see that PageHip has been enabled for readfile.exe over here. So now we can go ahead and we can fuzz our program, but before that we need to make sure that everything is working fine. So we need to run WinAFL in debug mode. That will generate a log file that will help us in identifying if there is any error or everything is perfectly fine. So let's go ahead and check that. Now if you have followed the instruction given in prerequisite doc, you must have copied WinAFL and DynamoRio in your fuzzing directory, that is inside your C drive. So let's go ahead and see what does WinAFL contain, and then we will see what does DynamoRio contain. So in WinAFL, when you go, you can see that it contains a lot of folders, and the folder which we are interested in is bin32 and bin64. So if your system is 32-bit, then go to bin32, use all the executable over here. If your system is 64-bit, then go to bin64 and use the executable from here. But for the sake of simplicity, let's use bin32. And when you go to bin32, you can see that it contains a lot of executable like AFL analyze, AFL fuzz, AFL show map, AFL tmin, and etc. So the file which we'll be using for fuzzing is AFL fuzz.exe, and that is what we'll be needing over here. And as I have mentioned, there is a DLL, that is winafl.dll. so this is actually a client DLL which takes care of all the instrumentation code. If you want to know more, the source code is available in the folder, so you can actually go through that, like aflfuzz.c, or there is winafl.c, so you can actually go through that. But right now we will simply see how do we use winafl, and we'll not be going to the source code. So this is what WinAFL contained, and let's go and see what does DynamoRio contain. So in DynamoRio directory, you can see that it contains couple of folder, and as we have seen, depending upon your system configuration, you can use any of this folder. So if your system is 32-bit, then go to bin32, otherwise go to bin64. So you can see it over here, a file name drrun.exe. So as I mentioned, this is the file which is responsible for doing runtime instrumentation, and so you need to give the path of this bin32 to WinAFL. So WinAFL has a specific command line option which we'll be discussing next. So if you want to run WinAFL in debug mode, let's go ahead and see what kind of command line option you need to give. So this is the command line which you can use to run WinAFL in debug mode, and what this command will do is that it will make sure that your target runs perfectly fine under Dynamorio. So it will actually generate one log file which give you a variety of info. I will be showing you after we run this command in during the hands-on. And as you can see, the syntax for this is pretty simple. You need to run this command from your bin32 or bin64-bit directory from your WinAFL folder. And as you can see, you need to give full path to your drrun.exe file, and then it expects one command line argument, that is C, which says that winafl.dll. So it means that drrun.exe is expecting client as winafl.dll. And as we have discussed in the past few slides, WinAFL will actually takes care of all the instrumentation and coverage related work from drrun.exe. And then there is another option, that is debug. So what it does is that it will generate a log file which we can have a look to make sure that everything is working fine. And then there is another option, that is target module, and target module is actually the name of the executable which contains your target function. So in case you write some harness, then you need to give that executable name after which you get after compilation over here in target module. And then there is another option, that is target offset. So target offset is the offset of your first function, which we have seen in the last few slides. We have used WinDBG to figure out the offset of that function. So in our case, this will be the offset of process image function, which was 10A0. And then there is another option, that is fuzz iteration. So that is 10. So fuzz iteration, what does it means is that WinAFL will start instrumenting your target module, then it will reach to the target offset, and then it will call pre-fuzz handler that will actually save the state of your system, and then it will let your first function execute, and if it crashes or hangs or whatever, and then as soon as this function finishes execution, it will call post fuzz handler. So that will actually restore the state of the system to the like it was before starting this or executing this function. So what does fuzz iterations means over here is that the same process will be repeated for 10 times. So it means that for 10 times it will call pre-fuzz handler and it will call post-fuzz handler. After that, you can see another argument, that is anargs. So it means the number of arguments your function expects. In our case, it will be only one, because process image expects only one argument, that is name of the file, and then hyphen hyphen, you can see name of the executable, that is target module, and followed by some input test file. So when you run this command, it will generate a log file, and which will be very helpful in identifying if you are facing any issues. If WinAFL is not working properly, then you can debug it from there. So let's move on and see a demo of that. As you can see, this is the command. So now let's go ahead and run this command and see what kind of debug log it's generated. So I am inside my WinAFL bin32 folder, and let me copy paste this command over here, and let's click enter. So make sure that this test file exists inside your bin32 folder, and as you can see that it has executed our sample program for 10 times, as you can count it over here. This is because we have given 10 as fuzz iteration. And now let's go ahead and see the debug log which it has generated over here. So you can see this is the debug log. It follows the naming convention as AFL dot your target executable name and then some value. So let's see what does it contains. And as you can see, we are seeing a lot of messages like module loaded. So first it is loading readfile.exe, then couple of Windows DLL over here, winafl.dll over here, and then you can see that in pre-fuzz handler, then it is opening the file, that is it is reading image.file, which we have given as a test input file. Then it is inside post fuzz handler, and same sequence is repeated for 10 times in pre-fuzz handler, open file, and post fuzz handler. And then you can see over here coverage map follows, and there is a message which says everything appears to be running normally. What does it means is that the program is working perfectly fine under Dynamo Rio, and whatever offset we have given over here, that is 10A0, and executable file name and everything is working fine. So we can go ahead to the next step and we can fuzz our program using WinAFL. So let's first see what are the parameters and command line option we need to give when we want to fuzz a program using WinAFL. So you can see this is the command line syntax. You need to type EFL first.exe followed by argument for EFL.exe and hyphen hyphen, then you need to give instrumentation options, that is for Dynamo, and then hyphen hyphen program name followed by any argument which program expects and followed by at symbol 2 times. So let's go ahead and have a look at what are the different arguments. We will start with the argument which AFL first.exe expects. So I will come to this m and s argument later on. First, let's see what are the other arguments. So there is I, that is similar to AFL first on Linux. It means input directory, which contains your input seed corpus. Then there is O, which is for output directory. This is again same as what we have seen on Linux. It means where AFL first will save all the crashes or hangs or other data. And the argument which is different over here is capital D. It means that you need to give Dynamo Rio bin32 or 64-bit directory path over here. So as you can see it over here, whatever folder you have copied your Dynamo Rio, you just need to give bin32 or bin64-bit path over here so that it can locate drrun.exe and it can do runtime instrumentation. Then this TI, that is for timeout. This is again same as Linux. And coming back to this m and s, so as I have shown in Linux, that is part 2, you can run AFL or WinAFL. You can run multiple instances of that. So you can run one master and n number of slaves depending upon the CPU cores you have. So if you want to run it in master and slave mode, then you can use m and you can give name of the master. It can be anything like master or m1 or whatever you prefer. And s means slave instance, so it can be any name like slave1 or s1 or whatever you prefer. So this master and slave can sync up with each other and they can help you in finding crashes or bugs in a short amount of time. And then the second options are for instrumentation option, that is Dynamo instrumentation options. And for that you need to provide few options because Dynamo cannot instrument entire program or entire files. So what you have to give is, first thing you need to give coverage module. So it is the name of the DLL or exe which you want to be instrumented, like gdi32.dll or msrd3x40.dll or whatever DLL you want to fuzz. You should write the name over here. And then there is another option, that is target module. So as we have discussed in our last part, it should be the name of your harness executable or name of the executable which contains your target method or target function. Then you can use any one of these, that is target method or target offset. So if you have symbol support, then you can use the function name. Like in our case, we can simply give, like, instead of target offset, we can use target method as process image. In case you don't have symbol support, then you can use target offset and you can give offset of the function. This is actually offset of the first function, which you can figure out by using WinDBG or any other techniques which you are familiar with. Then another option which you need to specify is call convention. So this is actually function calling convention on Windows. It can be any one of following, like this call, std call, cdeclare, fast call. So this is something which you can figure it out depending upon your system architecture and based on the program which you are fuzzing. So generally it should be this call or cdeclare or std call, any one of the following. And after that you need to give third argument, which is program arguments followed by @@. So after that you need to mention your program name. In our case it is readfile.exe, and since it doesn't expect any other command line option, we can simply add @@ symbol over here. So at runtime, WinAFL will replace this @ symbol with the actual first file name and it will start fuzzing. So now let's go ahead and fuzz our readfile.exe program and see what kind of crashes we get. So let's see. As you can see that this is the command line option which we need to use if you want to fuzz any program with WinAFL. There are three different parts. Part 1 is AFL first parameter. Part 2 is Dynamo parameters, that is coverage module, target offset, fuzz iteration. So this fuzz iteration, what does it means is that WinAFL will execute your target function for 5000 times, and then it will kill entire process. It will start a new process, and then it will again repeat the same cycle over here. And there is coverage type age or block. So there are two types of coverage. One is block based coverage and second one is age based coverage. So generally age based coverage gives better result, and then you need to use your executable name and followed by any argument or @@. So let's go ahead and fuzz our program, and we need to give an initial input file. So for that, what you can do is you can simply have one text file which contains nothing but simply like image data. You can simply create one text file as we have done on Linux. So this is our input seed file, and I will just paste the command over here. If you are following me along, then please paste this command, and let's see. As you can see that AFL is started fuzzing that, and it already found one crash over here. So the status screen of WinAFL and AFL is similar. There is no major change over here except the name over here, and rest everything is same. And you can see that current strategy it is trying is interest, then havoc, and speed we are getting is varies from like 1 execution per second, below that as well, to some 30 or 40 executions per second. And it has found, as of now, there are only 2 total paths. There is one unique crash, but there are 5 total crashes out there. And so let's wait for some time till it finds any new path or any new crash, and then we will see how do we do crash triage and root cause analysis. As you can see, it has found one more crash. So right now total unique crash are 2, and total crashes are around 38. So now I'm going to stop it over here, and we will move to the next part, that is crash analysis using WinDBG, and we can also use Visual Studio. So let's go to that. Now let's go ahead and debug our simple C program with the input we have found through WinAFL. So you need to go to debug in Visual Studio and go to read file properties, go to configuration properties under debugging. Simply gives the full path of your crashing file. In our case, it is ID 000000_00, and press F10. You can keep a breakpoint on main so that we can debug it. We will do step in and step out in most of the cases. So let's press F10 and then F11 for step in inside process image function, and let's press again F10. So as you can see, it is opening the file which we have given over here. It is doing some sanity checks if it is able to open file or not. So in this case, file open was successful, and then it is reading the value from the file. It is printing the data, and the same logic which we have seen in part 2. Size 1 is equal to image width plus image height. So as you can see, size 1 is large value, but malloc was successful, so there should not be any issue over here. Let's move on. It is checking if size 1 is equal to 5678, and in this case it is not. Size 1 is equal to 1 2 3 4 5 6, again it is not. And it is calculating size 2, again I don't see any issue over here. Size 3, it is getting image width divided by image height, and let's see. So size 3 is 0 now. And if you remember, same thing we have seen in part 2 when we have first this program using AFL on Linux. So this is the same case over here, and as you can see, buffer 4 is getting allocated by a malloc call, to which size 3 is getting passed as a parameter. So size 3 is 0. So when you pass 0 as an argument to malloc, it will be 0, it will return null. So buffer 1 buffer 4, sorry, will not be allocated. It will point to null. And let's see, when you copy some data to this, it will be an access violation, right? Because you are copying 10 bytes of data to an unallocated buffer. So this is the same issue which we have already seen on Linux using GDB. And so let's move on and see another crash. Again, we'll go and we will change the file name. We'll just change it to 1. And let's see. Debug it again, F10. And let's again do step in, step out. So you can see the same issue over here. In this case, size 3 is 1, and when you copy 1 byte of data, sorry, when you copy 10 bytes of data to a 1 byte of buffer, you will get access violation, writing location over here. So both are the same issue. Now let's go ahead and use WinDBG to debug these issues. Let's open WinDBG first, and let's open our executable file, that is readfile.exe, and we need to give path and file name of our crash file which we want to analyze over here. So inside argument option, just give the full path and file name, that in our case is id 0000000, and click on open. So you can customize WinDBG as per your needs. You can go to view and you can customize it. So I generally use disassembly and command and memory, but based on your preference you can use it whatever you want. You can also drag around this windows. So now let us set a breakpoint first. So for that we will use a command, that is bp, our file name, that is readfile exclamation mark and process image function, and then type G, that means go. So as you can see that our breakpoint has triggered over here and the program execution has stopped at process image function. So what you see over here is the disassembly of the code, and as you might have guessed if you take a look at the code, that there are some calls like fopen or free or fread malloc, etc. So this is something what we have seen during our debugging at Visual Studio. This is actually when you compile C code, you see something like this in disassembly. So now we will do step. So we will execute each instruction one by one and we will see what is happening over here. So for that the command is p, that is step. So just type p and click enter, press enter, and as you can see there is a fopen call over here, and after that there is a printf call which actually prints our basic string like width, height, header, etc. And you can actually use IDA Pro to see the disassembly, to do a bit of static analysis, and there are some plugin as well which combines both WinDBG and IDA like RedSync. So that is RET_SY and C. So as you proceed in your WinDBG debugging, that can be updated on IDA. But since this is a very simple program, you don't need that. So let's go ahead. You can see there is a fret call. It means that it is reading some data from the file. And then there is a free call over here. And you can see there is a malloc call. So let's see what is the argument being passed to malloc over here. You can see it's pushed ebx over here before malloc call. And if you check the value of ebx, it is like 513A5150. So what happens is that when you call malloc, the return address, the memory which gets allocated will be saved in EAX. So in this case, let's see. Okay, so as you can see, the EAX value has been changed. Now let's go to this memory location and see what is there. So as you can see, it contains C0C0. It means that it is a newly allocated memory. And you can also use a command that is heap and P and EAX. So this will give you some info on the heap, what is the size, etc. So as you can see, the user size over here is 513A5150. This is something which we have passed to the malloc over here. It was the same as what does EBX contain. So this is the size, and you can get various detail from the call stack over here, as you can see. So let's move on. So this will be useful while debugging a real vulnerability. Let's again type P and press enter, and you can see that there is another malloc call over here. So if you remember the source code, there was two variable which are like size 1, size 2, size 3. So this seems to be size 2, and the value is something which is like 170064. As you can see, push EAX over here. So this is the argument to malloc, and it contains this. So this much amount of memory will get allocated. So just step over, or just step again P command and press enter, and you can see there is a ID structure over here. So if you remember, in the source code, size 3 is getting calculated by dividing width by height, and so this is what the size 3 over here. And as you can see that ESI over here contains 0, so the value will be saved in EX, and then it will be transferred to ESI. So that is 0, as you can see it over here. And then there is a malloc call. So as we already know now that in the C code there is a variable named size3 whose value will become 0, and then it will be used to allocate a memory. So same thing is happening here. This is the assembly equivalent of that code over here. So you can see malloc 0, and it allocates some memory by default. So let's see what does EX contain. And if you go ahead and see, you can see that there is a 8 bytes in memory allocation over here. This is by default. And let's move forward now. So you can see that there are some move instruction, and at this location EAX plus 8, some data is being copied. But if you check EAX plus 8, it means this location it is not accessible. So we should get an access violation error over here. Yes, as you can see it over here, there is access violation. This is because this memory is not accessible, it is not allocated. And so this was the root cause. As we have seen, the malloc is being passed as 0 size, and some data is getting copied to that. So this is how you can do a basic root cause analysis using WinDBG as well. And I'm not going to debug second crash using WinDBG because both the crashes are same. So I hope that this has given you a decent understanding of how do you debug program using WinDBG. Although this is very basic, but you can try more, and that way you can learn. So with this, let's go to our next topic. So AFL and WinAFL status screen are same, so we can skip that. And crash analysis we have already done now. So let's see what we have learned so far. We have seen that how do we check if everything is working properly under WinAFL, if our program is getting instrumented properly or not. When you run WinAFL in debug mode, it generates a log file. So we can go to that and we can check. And then we have also first a simple C program using WinAFL, and we have also done crash analysis using WinDBG and Visual Studio. So With that, let's move on to next topic, and that is fuzzing real-world software. Now that we have seen how do we fuzz a simple C program using WinAFL on Windows and how do we do crash analysis using WinDBG, it is right time to try and fuzz a real-world software. So what you see on the right-hand side is a simple harness program. I would like all the attendees to go through that and understand what it does, and then we can discuss this further after a few minutes. So as you can see it over here, it's a very small program. There is a main function which again expects two argument argc argv, and then it calls the function fuzzme from the provided argument, that is a file name, a db file name. And inside the fuzzme, what it does is that it creates one cdao database object, and then it uses the open call to open the particular file name which we have passed as a parameter to this, as an argument to this program, and then it simply closes that and then function returns. So this is a very simple harness to fuzz mdb files, and as a input set corpus you need to provide various mdb files to that. And when I first did software around 2 years back, it actually resulted in 13 cvs. As you can see, it was a very small program, hardly maybe around 15 or 20 lines of code at max, but it actually resulted in a lot of cvs. And what I have found is that most of the crashes belongs to msrd3x40.dll file. And when you do a db.open over here for a particular file name, so the functions from this DLL will get called and they will parse your mdb file, and that's where a lot of vulnerabilities were found. So if you want, you can compile this C code and you can collect some mdb files from Google, and then now you know how to use WinAFL, so you can try fuzzing that and see if there is any new crashes which you can get over here. And with this, let's move on to our next topic. So this is one of the CVE which was present in MDB file. It was actually not found using the previous harness, which is this one. This is something which has been disclosed by ZDI, and we will discuss what was the root cause for this CVE and how it resulted in another CVE. So as you can see the description over here, it is an out of bound write vulnerability, and it was in processing of MDB files, and MDB files are actually database files which are used by MS Access. Older version of MS Access uses that. So it actually contains database structures like table, fields, and indexes, and it's a very old and proprietary file format, so there is no public specification which were available for that at that time. But there are many people who have spent their time in understanding the file structure of, and they have actually documented its structure. So if you want to know more details, you can go to this URL and it will give you more details. So MDB files actually follow a page structure, so it is a collection of pages. There will be different types of pages like first page, table definition page, data page, OLE fields, table property, etc. So it actually makes it a very easy first target. And so what happened is that there is a public POC available which is released by ZDI over here, and it actually contained two files. One is named as group1 and second one is poc.js file. So group1 was actually MDB file, and I have posted a blog on that over this URL. So I will be quickly covering through the root cause, what was the issue for this. So when you pass this group1 MDB file, what you will find is that it follows a specific structure as we have discussed over here, and the vulnerability was actually in the table definition page. So a table definition page follow this particular structure where initial 2 bytes will be 0201, then there are 2 bytes which is 5643, that is actually VC, and then there are various fields over there. So fields which we are interested in are these two, index count and real index count. So what happened is that every MDB file can have few indexes. So in this case, index count field will tell how many indexes are there in the file. And when you pass this file further, you will notice that each index follows a specific structure. So what you see over here is the structure of that index. Like it starts with an index number, then there is an index column number, and then there are various fields over here. So the value or field which we are interested over here is index 2 and the index number of that, which is 00230000. So what happens is that each index number has a name. So that is in again another structure where as you can see it over here, there is a name length and then there is actual strings like id over here. Then for second index it is length is 0c and the name is parent id name. So when you run this POC, when you open this JS file under a debugger WinDBG, you will see a crash something like this over here. So you can notice over here that ECX actually contains 0002300. So this is actually the index number over here. And when you look at the code over here, the assembly code over here, you can see that the program is trying to access some memory at a particular index over here. So EDX, if you see, is pointing to some memory location, and ECX is getting multiplied by 4 for each variable. And then 574 it gets added to that. So ECX actually work as a counter. And let's move on. We will further see over there. So when you look at the memory pointed by EDX plus 574 plus 0 or plus 4, what you will notice is that the total memory allocation was actually 128 bytes up to over here. And so what it means is that ECX was actually the index number, and for each index 4 bytes will be saved over here. And what are these bytes? They are actually the address of index name. So there will be an address over here which will actually point to the index name over here. So since the memory was allocated only for 32 indexes, this is because there are the maximum number of index can be only 32 in a MDB file. But in case if the index number is more than 32, then what will happen in this case is that it will get multiplied by 4, and then the program will try to write out of bound over here. So this was actually an out of bound write, because when you multiplied index number with ECX, that actually become very large number. In this case, when you multiplied ECX, that is 2300 by 4, it becomes very large and it cannot accommodate in, it cannot come inside this memory. So this was actually the root cause. And if you want to know more details, more in-depth analysis, you can actually go to the blog URL over here. That will give you more idea. And with this, what we have found is that how this issue was fixed is that there was a simple check which used to compare ECX with 0FF, that is 256. So this was actually not a proper fix, because if you change the value of FF to anything, something like say 20, because we know that the maximum indexes which is allowed is only 32, and index number starts from 0, so it can be from 0 to 31. But in case you use index number as 20, then it will corrupt some data at 128 plus 4th byte. So this actually resulted in another CVE which we actually found using WinAFL as well as manual analysis. So I have written a detailed blog on that as well over here. If you want, you can go to this URL and you can read this blog over here. And so finally how it was fixed is that there was a check which was added that if index number is more than or equal to 20, then the control is to transfer at another location, which used to generate a error message that MDB file is not valid. So this is how this issue was fixed. Now next move to next part, that is crash triaging on Windows. As we have discussed in part 2, manually it's very difficult to analyze each and every crash, because when you fuzz a software, you may get hundreds or thousands of crashes. So on Windows, you can use a tool called Bug ID for crash triaging, and you can also write your own tools, something like using Python and WinMDBG, or You can use any of your preferred language and you can automate this task. We will not be discussing much of the crash tracing over here because we have already discussed that in part 2. So let's move to the next part and see what we have learned as of now. So we have learned how do we fuzz real life programs on Windows, like how do we fuzz MDB files or how do we fuzz HDB files. And we have also discussed about root cause analysis of two vulnerabilities, which is CVE 2018 8423 and CVE 2019 0576. We have also discussed about crash sizing on Windows. With that, let's move to the last part, that is conclusion. So fuzzing is helpful in overall understanding of software security. It can help you to write better code. It can also help to find issues which cannot be found using normal testing. Fuzzing can help in securing software, and fuzzing should be part of software development lifecycle. But fuzzing requires a lot of hard work. Sometimes you get broken and non-working stuff, and you need to spend countless hours in analyzing issues and fixing them. Many times what happens when you fuzz a software, you face a lot of issues like missing libraries or some broken stuff, something is not working, so you have to spend a lot of time on that. And then you also need to do multiple vendor follow-ups, and you can also face rejection in case you have reported some issues to a vendor, and if he declines to fix that, then you might face such rejection when you report bugs, but that is okay. And in the end, fuzzing, it's worth it, so you should give it a try. With that, I conclude my training on fuzzing and finding vulnerabilities using AFL and WinAFL. I am thankful to all of you for attending my training today. I am also thankful to GrayHat for giving me this wonderful opportunity to provide my training. I am looking forward to provide more such training in the future. And in case you have any comments, questions, suggestions, or feedback about today's training, feel free to reach out to me. I can be reached by email, or you can also send a direct message to me on Twitter. With that, thank you everyone and have a nice day and enjoy GrayHat 2020. Goodbye. Thank you.